Dark matter and dark energy are two of the biggest mysteries in the universe. They make up around 95% of everything, yet we can't see them, touch them, or directly detect them. In this video, we're going to explore everything we know about these enigmatic forces that shape the cosmos. Let's start by breaking down what dark matter and dark energy are. Dark matter is believed to be an invisible form of matter that doesn't emit, absorb, or reflect light, but its presence can be inferred from its gravitational effects. On the other hand, dark energy is a mysterious force driving the accelerated expansion of the universe, pushing galaxies apart at an increasing rate. Although dark matter and dark energy seem similar because they're both dark and invisible, they behave very differently. Dark matter clumps together and helps form the structures of galaxies, while dark energy seems to work against gravity, stretching the fabric of space itself. Together, they dictate the evolution and fate of the universe. The concept of dark matter first emerged in the 1930s, when astronomers noticed something strange. Fritz Zwicky observed that the mass of certain galaxy clusters was far greater than what was visible. This invisible mass, which we now call dark matter, seemed to be holding galaxies together, preventing them from flying apart. Later, in the 1970s, Vera Rubin provided more evidence when she studied the rotation of galaxies. The stars at the outer edges of galaxies were moving faster than expected, suggesting that there was much more mass present than what we could see. This unseen mass was what we now refer to as dark matter. Dark energy, however, was a much later discovery. In the late 1990s, two independent teams of scientists studying distant supernovae made a surprising find. The universe wasn't just expanding, it was expanding at an accelerated rate. This discovery revealed the existence of a force that counteracts gravity, dark energy. We now know that dark energy accounts for about 68% of the universe, while dark matter makes up roughly 27%. That leaves only about 5% of the universe as the regular matter we can see, like stars, planets, and galaxies. The rest remains one of the greatest puzzles in modern physics. So how do we know dark matter is there if we can't see it? One of the strongest pieces of evidence comes from galaxy rotation curves, the way stars orbit the center of galaxies. If only visible matter were present, these stars should move much more slowly. The faster speeds imply the presence of an unseen mass, dark matter. We also see evidence of dark matter through gravitational lensing. This is when light from distant galaxies gets bent as it passes by massive objects, like galaxy clusters. The amount of bending we observe doesn't match up with the visible mass in those clusters, suggesting that there's more mass out there that we can't see. Dark energy, on the other hand, reveals itself through the expansion of space. By measuring the rate at which galaxies are moving apart, and by studying the cosmic microwave background radiation, scientists have pieced together the clues to its existence. However, we still don't fully understand what dark energy is or how it works. Dark matter is not made of the same material as the stars, planets, or even you and me. It's not composed of atoms, the building blocks of ordinary matter, which means it doesn't form atoms, molecules, or any of the elements we're familiar with. This sets it apart from everything we can observe directly. It's also not antimatter. Antimatter, while exotic, behaves in ways we understand. When it comes into contact with matter, it annihilates in a burst of energy, something we would have detected if dark matter were composed of antimatter. Yet, no such energy has been observed. Dark matter isn't like the black holes we know about either. Although black holes are massive and hard to detect directly, they interact with light by warping space around them. Dark matter, on the other hand, doesn't bend light in the same way, suggesting it's a completely different entity. Another thing dark matter isn't is normal gas or dust. While space is filled with various gases and particles, these materials still interact with light, either by absorbing it or emitting radiation. Dark matter does none of this, remaining completely invisible to our telescopes. It's also not just cold, regular matter that's somehow hidden from us. If dark matter were just distant, unseen planets, stars, or dust, it would still interact with light or gravitationally clump together in ways we could detect. Instead, dark matter is spread out and behaves in ways that don't match ordinary matter. Dark matter is not baryonic, meaning it doesn't consist of protons, neutrons, and electrons, the particles that make up regular matter. Baryonic matter forms the atoms in everything we see, but dark matter doesn't participate in these familiar interactions. This tells us it's something fundamentally different. It's also not light or any kind of electromagnetic radiation. All the forms of radiation we know, visible light, radio waves, X-rays, can be detected, but dark matter neither emits nor absorbs any of these. It's truly dark in every sense of the word, interacting only through gravity. Dark matter doesn't form stars or planets. It doesn't clump together the way normal matter does to form celestial bodies. Instead, it stays diffuse, meaning it spreads out and forms massive halos around galaxies, affecting their structure but not producing the bright objects we see in the sky. It's important to understand that dark matter isn't a type of energy either. While dark energy drives the expansion of the universe, dark matter is something much more material in nature, providing gravitational glue. It's a form of matter, even if it doesn't fit into the categories we're familiar with. Scientists are confident that dark matter isn't composed of particles we know, like photons or neutrinos. Neutrinos are tiny, nearly massless particles that rarely interact with anything, but they don't have enough mass to account for dark matter. Whatever dark matter is, it's much heavier and interacts even less. The idea that dark matter is simply a misunderstanding of gravity has also been largely ruled out. Some theories suggest modifications to gravity could explain the phenomena attributed to dark matter. However, these theories struggle to explain all the evidence we've gathered, especially on large cosmic scales. Lastly, dark matter isn't something that we can currently see or touch in any direct way. While we're surrounded by it, and it affects the universe on a massive scale, no experiment has yet been able to capture a dark matter particle. It remains elusive, but it's certainly not just another form of the matter we already know. Dark matter plays a crucial role in shaping the universe, primarily through its gravitational influence. Even though we can't see it, we can observe how it affects the movement of galaxies and galaxy clusters. Without dark matter's gravity, galaxies would not be able to hold themselves together. The most direct evidence of dark matter's gravitational pull comes from the rotation curves of galaxies. Stars at the outer edges of galaxies move faster than expected based on the visible matter alone. This suggests there's an unseen mass providing the extra gravitational pull. In galaxy clusters, dark matter's gravity also has a profound effect. The visible mass in these clusters isn't enough to explain the speeds at which galaxies within them move. The additional mass provided by dark matter helps keep these clusters gravitationally bound. Gravitational lensing is another phenomenon that reveals the presence of dark matter. When light from distant objects passes near a massive object, like a galaxy cluster, it gets bent. The amount of bending we observe often exceeds what can be explained by visible matter alone, pointing to the presence of dark matter. This bending of light helps scientists map the distribution of dark matter. Even though it's invisible, its gravitational effects can be traced, showing where the dark matter lies. These gravitational maps give us a clearer picture of how much dark matter is present in different parts of the universe. In large-scale cosmic structures, dark matter's gravitational influence is even more apparent. It helps form the scaffolding on which galaxies and galaxy clusters build. Without dark matter, the universe would look much different, with less structure and fewer galaxies. Dark matter also prevents galaxies from tearing themselves apart. The mass from ordinary matter alone wouldn't be enough to keep galaxies intact over billions of years. Dark matter's gravitational pull provides the necessary glue to hold galaxies together as they spin. The gravitational effects of dark matter aren't limited to just galaxies and clusters. On even larger scales, dark matter plays a role in shaping the cosmic web, the vast network of filaments connecting galaxies. This web wouldn't exist without the gravitational influence of dark matter. Cosmologists use dark matter's gravitational effects to understand the formation of the universe. During the early stages of the universe, dark matter provided the seeds for galaxy formation. Its presence allowed ordinary matter to clump together and form the galaxies we see today. In simulations of the universe, the presence of dark matter is essential for accurately modeling cosmic evolution. Without it, galaxies would not form in the same way. Dark matter's gravitational role helps create realistic models that match the universe we observe. Even though dark matter doesn't interact with light, its gravity still shapes the distribution of visible matter. It pulls gas and dust toward it, influencing star formation. This hidden mass helps drive the processes that give rise to the structures we see in the universe. Scientists believe that dark matter may even play a role in the formation of supermassive black holes. Its gravitational influence could help pull matter together in the early universe, leading to the formation of these cosmic giants. Though still a hypothesis, it's one of many ways dark matter's gravity shapes the cosmos. Dark matter is invisible because it doesn't emit, absorb, or reflect light. This makes it fundamentally different from the matter we're familiar with, which interacts with electromagnetic radiation. While stars, planets, and gas clouds can be seen by the light they give off or block, dark matter remains completely hidden. Its lack of interaction with light is one of the biggest challenges in studying dark matter. Unlike ordinary matter, which can be observed through telescopes at various wavelengths, dark matter doesn't appear in any part of the electromagnetic spectrum. Whether we use radio waves, visible light, or X-rays, dark matter stays undetectable through these methods. Despite being invisible, we know dark matter is there because of its gravitational effects. It has mass and creates a gravitational pull, but it doesn't react with photons. This means we can't observe it directly like we would a star or a gas cloud, but its presence is inferred from how it influences the things we can see. Another key feature of dark matter is its non-interaction with ordinary matter. It doesn't collide with atoms or particles in the same way that other forms of matter do. This lack of interaction means dark matter can pass right through regular matter without leaving a trace. Even though dark matter fills the universe, it's effectively invisible to all our current detection techniques based on light. It doesn't get absorbed by stars or trapped in black holes because it doesn't respond to electromagnetic forces. This makes it incredibly elusive and difficult to detect with standard tools. Because dark matter doesn't interact with light, it also doesn't heat up or cool down in the same way as ordinary matter. It doesn't radiate heat or energy as it moves through space, so it remains undetectable through thermal imaging. Its temperature, in this sense, is irrelevant to our usual methods of observation. Its invisibility also means dark matter doesn't emit any signals or signatures we could detect with traditional telescopes. Ordinary matter, when heated or excited, releases energy in the form of light or radiation. Dark matter, on the other hand, remains silent, making it even harder to study. This non-interaction with light is why dark matter can't be found using direct imaging. Telescopes and detectors that rely on photons are simply blind to dark matter's presence. No matter how powerful our instruments get, they won't see dark matter directly because it doesn't produce light. Some might wonder if dark matter could be made of extremely faint or distant objects, but even those would emit some kind of radiation. Dark matter, however, leaves no such trace. Its complete lack of electromagnetic interaction confirms that it's not just made of dim stars or cold gas clouds. Because it's invisible, scientists have to rely on indirect methods to detect dark matter. The most effective approach is studying its gravitational effects on visible matter. When we see galaxies behaving in ways that regular matter alone can't explain, we know dark matter must be present, even though we can't observe it. While dark matter doesn't interact with light, it still influences the overall structure of the universe. Its gravity affects how galaxies form and cluster together, shaping the large-scale patterns of the cosmos. Without its gravitational pull, the universe would look very different, even though we can't see dark matter itself. The fact that dark matter doesn't emit or block light helps explain why it's been so difficult to detect. We've built our entire understanding of the universe on observing light, but dark matter defies this method. It forces us to think beyond the visible and explore new ways to uncover the unseen forces shaping the cosmos. One of the strongest pieces of evidence for dark matter comes from studying how galaxies rotate. When we observe the stars at the edges of galaxies, we notice they're moving much faster than they should be if only the visible matter were influencing their motion. This discrepancy suggests there's an unseen mass providing additional gravitational force. According to the laws of physics, stars farther from the center of a galaxy should move more slowly, just like planets in our solar system. But observations show that stars at the outer edges maintain high speeds, as if something else is pulling on them. This extra gravitational pull points to the presence of dark matter. If galaxies were made up of only the visible matter we can detect, these outer stars would either slow down or the galaxies would fly apart. Instead, They continue moving rapidly, implying that there's a huge amount of invisible matter surrounding the galaxy, holding it together. This discrepancy between expected and observed rotation speeds was first identified in the 1970s by astronomer Vera Rubin. Her work on galaxy rotation curves provided crucial support for the existence of dark matter. She found that the mass we can see, stars, gas, and dust, only accounts for a small fraction of the total mass needed to explain the rotation. The difference between the visible mass and the total mass inferred from the rotation curves is often referred to as the missing mass problem. Dark matter is thought to make up this missing mass, providing the gravitational pull necessary to explain the movement of stars at the edges of galaxies. Rotation curves of spiral galaxies offer consistent evidence across the universe. Regardless of a galaxy's size or shape, the pattern is the same. Stars at the outer edges rotate faster than they should. This consistency strengthens the argument that dark matter is a universal component of galaxies. Without dark matter, the speed of these stars would slow down significantly at greater distances from the galactic center. But the fact that they continue moving quickly indicates that dark matter extends far beyond the visible edges of galaxies, forming a halo that we can't directly observe. These dark matter halos are thought to be much larger than the galaxies themselves. While the visible part of a galaxy is relatively small, the halo of dark matter surrounding it is vast and massive, providing the necessary gravitational support. This explains why the rotation curves remain flat, even at great distances from the center. Further evidence comes from studying galaxies in different environments. Whether isolated or in clusters, their rotation curves exhibit the same behavior, suggesting that dark matter is a fundamental part of galaxy formation and structure. The amount of dark matter present appears to be proportional to the galaxy's size. Computer simulations of galaxy formation also rely on dark matter to match observed rotation curves. When dark matter is included in these models, the resulting galaxy structures and rotation speeds align with what we see in the real universe. Without dark matter, the simulations fail to produce realistic galaxies. This evidence from galaxy rotation curves is one of the most compelling arguments for dark matter's existence. It provides a clear, observable phenomenon that can't be explained by visible matter alone. The invisible mass revealed through these curves is crucial to our understanding of how galaxies behave. Although we can't see dark matter, its effects on galaxy rotation leave little doubt that it's there. The consistent mismatch between visible mass and gravitational effects is a strong indicator that something unseen, something massive, is at work in shaping the universe. Dark matter makes up about 27% of the total mass and energy in the universe. This might not seem like a huge number at first glance, but when you consider that ordinary matter only accounts for around 5%, the significance of dark matter becomes clear. The vast majority of the universe is made of things we can't directly see. When scientists measure the amount of dark matter, they use a variety of techniques, like observing the motion of galaxies, studying the cosmic microwave background, and looking at gravitational lensing effects. All of these methods point to the same conclusion: dark matter is far more abundant than regular matter. One of the most remarkable findings is that dark matter is spread throughout the universe, not just clustered around galaxies. It forms a vast cosmic web, connecting galaxies and clusters together. This web is critical for understanding how the universe's large-scale structure has evolved over billions of years. Without dark matter, the universe would look very different. The amount of regular matter alone isn't enough to explain how galaxies and galaxy clusters formed. Dark matter's gravitational pull helped ordinary matter clump together, allowing these massive structures to emerge. The total amount of dark matter is key to our understanding of cosmic evolution. During the early universe, dark matter played a significant role in the formation of the first galaxies. Its presence allowed regions of higher density to collapse under gravity and form stars, galaxies, and other cosmic structures. Although dark matter dominates the mass of the universe, it doesn't interact with the ordinary matter we know. Its abundance explains why galaxies are able to exist in their current form, but its elusiveness makes it one of the greatest mysteries in cosmology. Despite its abundance, we still can't directly detect it. By studying the cosmic microwave background, the afterglow of the Big Bang, scientists have been able to estimate the total amount of dark matter with incredible precision. These measurements reveal how much dark matter was present in the early universe and how it has shaped the universe over time. The distribution of dark matter throughout the universe is not uniform. It tends to clump together in certain regions, creating massive structures where galaxies form. These dark matter concentrations act like cosmic scaffolding, helping to guide the formation of galaxies and clusters. Clusters of galaxies provide another way to measure the amount of dark matter. When astronomers observe these massive clusters, they find that visible matter only makes up a small fraction of the total mass. The rest, roughly 85%, must be dark matter, holding the cluster together with its gravitational pull. Dark matter also affects the expansion of the universe. While dark energy is driving the universe to expand at an accelerating rate, dark matter's gravitational influence slows this expansion down. The balance between dark matter and dark energy is a crucial factor in determining the ultimate fate of the universe. Despite making up a significant portion of the universe, dark matter is incredibly difficult to detect because it doesn't emit or absorb light. This has led scientists to develop indirect methods of measuring its presence, focusing on its gravitational effects on visible matter and the cosmic structure. In terms of the universe's overall composition, dark matter outweighs regular matter by a factor of more than 5 to 1. This unseen mass is what holds galaxies and galaxy clusters together, and its sheer abundance shapes the universe on both small and large scales. It's everywhere, but it remains invisible to our eyes. The universe has been expanding ever since the Big Bang, but it's not just a simple outward movement of galaxies. What's surprising is that the expansion is speeding up over time, a discovery that shocked scientists in the late 20th century. This acceleration implies that some unknown force is pushing galaxies apart faster and faster. This accelerating expansion suggests that gravity alone can't explain what's happening on cosmic scales. Gravity, which normally pulls objects together, should be slowing the expansion down. Instead, there's something working against gravity, causing the universe to stretch at an ever-increasing rate. This mysterious force driving the expansion is called dark energy. Unlike dark matter, which holds galaxies together, dark energy works in the opposite direction, pushing space itself to expand. The discovery of this force transformed our understanding of the universe's future. The concept of an expanding universe was first proposed by Edwin Hubble in the 1920s, when he observed that galaxies are moving away from us. The further a galaxy is, the faster it's receding, suggesting that space itself is stretching. But Hubble's observations didn't account for the unexpected acceleration we now know exists. Dark energy is thought to make up about 68% of the universe, dwarfing both dark matter and ordinary matter. It's this vast presence that's responsible for the expansion getting faster. Without dark energy, the universe's expansion would likely be slowing down instead of speeding up. The discovery of the universe's accelerating expansion came from observing distant supernovae. These exploding stars serve as standard candles because their brightness tells us how far away they are. By comparing their distances with how fast they're receding, scientists realized the universe wasn't just expanding, but accelerating. The acceleration of the universe's expansion has profound implications for its future. If this rate continues to increase, galaxies will keep moving further apart, eventually becoming so distant that they're no longer visible. This would lead to a cold, dark universe, where stars burn out and galaxies drift apart forever. This ongoing expansion also affects how we view the universe's age. Since the universe is expanding faster than previously thought, scientists had to revise estimates of its age, currently placing it at around 13.8 billion years. The expansion is a critical piece in understanding the timeline of cosmic history. Even though dark energy drives the expansion, we still don't fully understand what it is or how it works. It's unlike any force we've ever encountered. Some theories suggest it could be a property of space itself, while others propose new, undiscovered particles or fields. The expansion of the universe is also connected to the cosmic microwave background, the faint radiation left over from the Big Bang. By studying this radiation, scientists can learn more about how the universe expanded in its earliest moments. This, in turn, helps us understand the role dark energy has played throughout cosmic history. As space continues to expand, the distances between galaxies grow larger. While this might seem abstract, it has real consequences for the fate of the universe. Over billions of years, the accelerated expansion will dramatically reshape the universe, with galaxies becoming isolated in vast empty space. The expansion of the universe is one of the most striking examples of how dynamic the cosmos truly is. What began as a singular event, the Big Bang, has turned into a continuous accelerating process that reshapes everything we know about space, time, and the ultimate destiny of the universe. Dark energy plays a crucial role in shaping the large-scale structure of the cosmos. It's responsible for driving the accelerated expansion of the universe, counteracting the gravitational pull of matter. As space expands, dark energy becomes more dominant, influencing the future evolution of the universe. One of the most important effects of dark energy is its influence on the fate of galaxies. As it pushes the universe apart, galaxies move away from each other at an increasing rate. Over time, this expansion will isolate galaxies, making it more difficult for them to interact and form clusters. Dark energy's impact extends to the cosmic microwave background, the leftover radiation from the Big Bang. By studying tiny fluctuations in this radiation, scientists can measure how dark energy affects the expansion rate. This helps refine our understanding of its role in the universe's history. In addition to shaping the universe's large-scale structure, dark energy affects the distribution of galaxies. The further galaxies move apart, the less gravitational influence they have on each other. This results in a more spread-out, less connected universe over time. Dark energy isn't just a distant cosmic force, it affects the universe on all scales. It influences how galaxies form and evolve, limiting the rate at which new structures can emerge. As dark energy's influence grows, it will become harder for galaxies to merge or form new clusters. The existence of dark energy has changed how we think about gravity. While gravity pulls matter together, dark energy pushes space apart. This delicate balance between the two forces has determined the universe's structure since its early days, and will continue to do so in the future. As dark energy becomes more dominant, it will slow down the formation of new stars. The expanding universe will cause galaxies to drift apart, making it more difficult for gas and dust to accumulate in sufficient quantities to form stars. This could eventually lead to a universe with fewer new stars and dimming galaxies. Scientists believe dark energy has been present since the beginning of the universe, but its effects were minimal in the early stages. Back then, the universe was much denser, and gravity played a more significant role in shaping its evolution. Only as the universe expanded and became less dense did dark energy's influence become more pronounced. The discovery of dark energy has led to the development of new cosmological models. These models help explain not only the current expansion, but also how dark energy may influence the universe's long-term future. Whether the universe will continue expanding forever or reach a different fate depends largely on how dark energy behaves over time. Some theories suggest that dark energy could eventually dominate the universe to such an extent that it leads to a big rip. In this scenario, the expansion would accelerate so dramatically that it would tear galaxies, stars, and even atoms apart. This represents one possible outcome for the universe, though it remains speculative. Despite its significant role in the cosmos, dark energy remains one of the least understood aspects of the universe. Scientists are still working to uncover its true nature, exploring possibilities like vacuum energy or a new field that permeates all of space. Understanding dark energy could unlock answers to some of the biggest questions in physics. As our understanding of dark energy evolves, so too will our view of the cosmos. It's a force that governs not just the present state of the universe, but also its past and future. The role of dark energy in shaping the cosmos may ultimately determine the universe's final fate. The cosmological constant is one of the simplest explanations for dark energy. It was first introduced by Albert Einstein in 1917 as a way to balance the equations of general relativity. At the time, Einstein believed the universe was static, so he added this constant to prevent it from collapsing under gravity. When Einstein later learned that the universe was expanding, he called the cosmological constant his biggest blunder. But decades later, it was revived as a potential explanation for dark energy. Today, it's a key component of modern cosmology, helping explain the universe's accelerating expansion. The cosmological constant represents a constant energy density that fills space uniformly. This energy exerts a negative pressure, which counteracts gravity and drives the expansion of space. In this model, the amount of dark energy per unit of space remains constant, even as the universe grows. One reason the cosmological constant is so appealing is its simplicity. It fits neatly into Einstein's equations of general relativity without needing to introduce new particles or forces. Despite its elegance, it raises deep questions about the nature of the universe and why this constant has the value it does. Scientists calculate that the value of the cosmological constant is incredibly small, but not zero. Even this tiny amount of energy is enough to influence the universe on large scales, causing galaxies to move apart at an accelerating rate. The mystery lies in why this value is so finely tuned to allow for the universe we observe. One way to think about the cosmological constant is as the energy of empty space, or vacuum energy. Even in a vacuum, space is not truly empty. It's filled with quantum fluctuations. These tiny, momentary bursts of energy may be responsible for the effects we attribute to the cosmological constant. However, the predicted amount of vacuum energy from quantum theory is vastly larger than the observed value of the cosmological constant. This discrepancy is one of the biggest unsolved problems in physics. It suggests that something fundamental about our understanding of space, energy, or both is missing. The cosmological constant also has important implications for the future of the universe. If dark energy remains constant, the universe will continue to expand forever, with galaxies drifting further apart over time. This leads to a future where the universe becomes increasingly cold, dark, and empty. While the cosmological constant is the leading explanation for dark energy, it's not the only one. Some scientists propose that dark energy might change over time, in which case the constant may not be so constant after all. These alternative models suggest that the expansion rate could vary as dark energy evolves. There's also the possibility that the cosmological constant is just a placeholder for something deeper. Some theories suggest it could be linked to undiscovered physical laws or new forms of energy. As we continue to study dark energy, we may find that the cosmological constant is only part of the picture. Despite its simplicity, the cosmological constant remains mysterious. It raises profound questions about the nature of reality, the fabric of space-time, and the fundamental forces governing the cosmos. Understanding its true origin could revolutionize our knowledge of the universe. For now, the cosmological constant provides a useful framework for explaining dark energy and the expansion of the universe. It fits within our current models, but the search for a deeper explanation continues. Whether it's truly constant or just a temporary solution is still an open question in cosmology. Vacuum energy is closely tied to the idea of the cosmological constant. It refers to the energy that exists in empty space, even when there's no matter or radiation present. Quantum mechanics tells us that space is never truly empty, as particles and antiparticles constantly pop in and out of existence. These quantum fluctuations give rise to a tiny amount of energy that fills all of space. In theory, this vacuum energy could be what's driving the accelerated expansion of the universe. It might be the physical basis for the cosmological constant, providing a possible explanation for dark energy. However, there's a significant problem when trying to match vacuum energy with the observed value of the cosmological constant. The amount of vacuum energy predicted by quantum theory is much larger than what we observe in the universe. This discrepancy is sometimes called the vacuum catastrophe. According to calculations, the vacuum energy predicted by quantum field theory should be about 120 orders of magnitude greater than what we observe. This means that if vacuum energy were really responsible for dark energy, the universe would be expanding far more rapidly than it is. Clearly, there's something missing in our understanding. One possibility is that the effects of vacuum energy are somehow being cancelled out or reduced by another mechanism. This could explain why the actual value of the cosmological constant is so much smaller than expected. But identifying what that mechanism might be remains one of the greatest mysteries in physics. The relationship between vacuum energy and dark energy also raises questions about the nature of empty space. If vacuum energy is real, it means that even a perfect vacuum isn't truly empty. Instead, it's filled with an invisible form of energy that influences the expansion of the universe. Despite the challenges, many scientists believe that vacuum energy plays a role in dark energy. The idea fits well with our current understanding of quantum mechanics and general relativity. However, reconciling the theoretical predictions with the observed data continues to be a major hurdle. The connection between vacuum energy and the cosmological constant could also have implications for particle physics. If we can understand how vacuum energy works, it might shed light on other fundamental forces in the universe. It could reveal new particles or fields that we haven't yet discovered. Some theories suggest that vacuum energy might not be constant, but could change over time. This would mean that the force driving the universe's expansion could evolve, leading to different rates of expansion in the future. Such a dynamic form of dark energy would challenge the idea of a fixed cosmological constant. In this context, the relation between vacuum energy and dark energy becomes even more complex. If vacuum energy fluctuates or changes over time, it could explain why the universe's expansion rate seems to vary across different epochs. This could also provide new insights into the universe's ultimate fate. The study of vacuum energy is a key area of research in both cosmology and quantum mechanics. It bridges the gap between the smallest scales of quantum particles and the largest scales of cosmic structure. Understanding this connection could unify two major fields of physics that currently seem incompatible. Ultimately, the relationship between vacuum energy and the cosmological constant could unlock new levels of understanding about the universe. Whether vacuum energy truly drives dark energy, or whether we need an entirely new theory, remains to be seen. But it's clear that vacuum energy holds a crucial piece of the puzzle. Dark energy makes up a staggering 68% of the total energy content of the universe. This means that more than 2/3 of the universe is composed of something we still don't fully understand. Despite its invisibility and mysterious nature, dark energy dominates the cosmos. In comparison, dark matter, which makes up 27% of the universe, and ordinary matter, at just 5%, play a much smaller role in the overall energy balance. This puts dark energy at the forefront of cosmic influence, driving the expansion and shaping the future of the universe. The discovery that dark energy holds such a large percentage was a complete surprise to scientists. Before the late 1990s, it wasn't even clear that the universe was accelerating in its expansion. When the acceleration was observed, it completely changed our understanding of the universe's composition. Cosmologists use a concept called the energy density of the universe to calculate the proportions of dark energy, dark matter, and ordinary matter. The energy density is essentially how much energy exists per unit volume of space. In this calculation, dark energy comes out on top by a wide margin. The fact that dark energy makes up such a large percentage has significant implications for the fate of the universe. Since it's the dominant component, its influence will only grow stronger as the universe expands. This could lead to a future where galaxies are pulled so far apart that they become isolated in the vast emptiness of space. Interestingly, the percentage of dark energy hasn't always been this high. In the early universe, matter, both ordinary and dark, was far more dominant. But as space expanded and became less dense, dark energy began to take over, becoming the primary driver of cosmic expansion. This shift in dominance from matter to dark energy is a relatively recent development on the cosmic timeline. For billions of years after the Big Bang, gravity from dark matter and ordinary matter held the universe's expansion in check. But now, dark energy is accelerating the expansion at an ever-increasing rate. The percentage of dark energy also helps explain why the universe looks the way it does today. If dark energy had been stronger earlier in the universe's history, galaxies and stars might not have had the chance to form. Its current strength has allowed cosmic structures to develop before accelerating the expansion. Measuring dark energy's percentage with precision is done using a variety of methods, including observations of supernovae, the cosmic microwave background, and large-scale structure surveys. These measurements consistently show that dark energy accounts for about 68% of the total energy content of the universe. As dark energy continues to dominate, it could eventually make up an even larger percentage of the universe's total content. As the universe expands, the relative amount of matter, both dark and ordinary, will decrease, while dark energy remains constant, meaning its influence will only grow over time. The vast percentage of dark energy suggests that our current understanding of the universe is incomplete. We've only begun to grasp the nature of this mysterious force, and its overwhelming presence points to a deep underlying feature of the cosmos that we have yet to fully explore. Dark energy's dominance in the universe not only drives its expansion, but also poses some of the biggest questions in modern physics. Understanding why it makes up such a large percentage of the universe could lead to new breakthroughs in our knowledge of space, time, and the fundamental laws of nature. Fritz Zwicky was a Swiss astronomer who, in the 1930s, made a groundbreaking observation that would later contribute to the discovery of dark matter. While studying the Coma galaxy cluster, he noticed something strange. The galaxies within the cluster were moving much faster than expected. The visible mass of the galaxies wasn't enough to account for these high speeds. Zwicky used a method called the virial theorem to calculate the total mass of the cluster. His calculations revealed that the visible matter, such as stars and gas, made up only a fraction of the total mass. This meant there had to be some unseen mass exerting gravitational influence, what Zwicky called dunkel Materie, or dark matter. This was the first time the term dark matter was introduced to describe an unknown substance that didn't emit light, but had a gravitational effect. Zwicky's work was revolutionary, but it didn't receive much attention at the time. His findings were considered controversial, and it would be decades before the idea of dark matter gained wider acceptance. Zwicky proposed that the missing mass could be in the form of invisible particles or some other form of matter that we couldn't detect with the technology available. He believed that this hidden mass was necessary to explain the stability of galaxy clusters. Without it, the galaxies would have flown apart due to their high speeds. Despite the skepticism around his work, Zwicky's observations were a critical first step in the study of dark matter. He was among the first to suggest that most of the universe's mass is not visible. His pioneering work laid the foundation for future discoveries in cosmology. Zwicky also made other important contributions to astronomy, including the concept of supernovae and the prediction of neutron stars. However, his work on dark matter is perhaps his most significant legacy. It challenged the prevailing ideas of the time and opened the door to a whole new field of research. The speed Zwicky observed in the Coma cluster could only be explained by the presence of a massive amount of unseen matter. This was a bold assertion, as it implied that our understanding of the universe's composition was incomplete. He wasn't just seeing ordinary matter. He was hinting at a cosmic mystery that still baffles scientists today. His calculations showed that the mass-to-light ratio in the Coma cluster was far too high to be explained by the luminous matter alone. This discrepancy was the first real evidence that something else was contributing to the total mass of galaxies, and Zwicky argued that this dark matter made up the difference. Zwicky's work also highlighted the need for more advanced tools and techniques to study the universe. At the time, astronomers relied solely on visible light, but Zwicky's findings hinted that other methods would be needed to detect this unseen mass. His observations encouraged future astronomers to develop more sophisticated ways to measure the universe. Though largely overlooked during his lifetime, Zwicky's observations are now considered a key piece of evidence in the dark matter puzzle. His work was far ahead of its time, and today scientists still rely on the basic principles he used to study galaxy clusters. He was a visionary, seeing beyond what others could imagine. Zwicky's idea of dark matter set the stage for later discoveries, including those of Vera Rubin and others, who found similar anomalies in galaxy rotation curves. His pioneering work helped establish the idea that dark matter is a fundamental component of the universe. Without Fritz Zwicky's early observations, the field of cosmology might have taken much longer to recognize the importance of dark matter. His contributions continue to influence modern astronomy as researchers explore the unseen forces that shape the universe. Vera Rubin was an astronomer whose work in the 1970s provided compelling evidence for the existence of dark matter. She focused on measuring the rotation curves of galaxies, specifically how stars orbit around the centers of these galaxies. What she discovered would reshape our understanding of the universe. Rubin expected that stars farther from the center of a galaxy would orbit more slowly, just as planets in our solar system do. Instead, she found that stars at the outskirts of galaxies were moving just as fast as those closer to the center. This defied expectations based on the visible mass of the galaxies. These high speeds couldn't be explained by the gravitational pull of the visible matter alone. According to Newtonian physics, the further a star is from the galaxy's center, the slower it should move, but Rubin's observations showed otherwise. There had to be something else providing the necessary gravitational force. Rubin's results pointed to the presence of a vast amount of unseen mass surrounding each galaxy. This invisible matter, now known as dark matter, accounted for the extra gravitational pull needed to keep the outer stars moving at such high speeds. Without it, the galaxies would simply fly apart. Her work built on Fritz Zwicky's earlier observations, but Rubin's galaxy rotation curves provided even more concrete evidence. While Zwicky had studied galaxy clusters, Rubin's focus on individual galaxies helped cement the idea that dark matter wasn't just a local phenomenon, but a universal one. The rotation curves Rubin observed were consistent across many galaxies, large and small. No matter where she looked, the pattern was the same. Outer stars moved faster than they should based on visible matter alone. This uniformity suggested that dark matter was a fundamental component of galaxies. Rubin's findings were met with skepticism at first, but over time they became a cornerstone of modern cosmology. Her meticulous observations and detailed data left little room for doubt. The concept of dark matter could no longer be ignored or dismissed as a fringe idea. What made Rubin's work so important was that it wasn't just a single anomaly or isolated case. The behavior she observed was repeated in galaxy after galaxy, indicating that dark matter was pervasive throughout the universe. This consistency made it clear that our understanding of matter in the cosmos was incomplete. Her work didn't just change how we view galaxies, it also influenced the way we think about the universe as a whole. Rubin's discoveries showed that visible matter makes up only a small fraction of the total mass of the universe, with dark matter being far more abundant. This was a major shift in perspective. Vera Rubin's research was groundbreaking not only for its scientific impact, but also for its rigor and precision. Her careful measurement of galaxy rotation curves set a new standard in observational astronomy, making her one of the most respected figures in her field. Her legacy continues to inspire astronomers today. In addition to revolutionizing our understanding of dark matter, Rubin's work highlighted the need for new theories and models in physics. The existence of dark matter challenges the foundations of our understanding of gravity and forces scientists to rethink how the universe operates on both large and small scales. Rubin's contributions to astronomy were profound, and her work remains central to the study of dark matter. Her observations provided a clear, consistent picture of a universe shaped by forces we cannot see, fundamentally changing the way we think about the cosmos. Gravitational lensing is another powerful piece of evidence for the existence of dark matter. This phenomenon occurs when the gravity of a massive object, like a galaxy cluster, bends the light coming from objects behind it. The effect is similar to a magnifying glass, distorting the light and creating multiple images or arcs of distant galaxies. According to Einstein's theory of general relativity, massive objects curve the fabric of space-time, and this curvature bends the path of light. The amount of bending depends on the mass of the object, but when astronomers observe gravitational lensing, they often find that the visible matter alone can't account for the amount of distortion. This discrepancy points to dark matter. The extra gravitational pull needed to bend the light as much as we observe must come from unseen mass. Dark matter, though invisible, exerts enough gravity to cause these lensing effects, providing a way to map its distribution in galaxy clusters. One famous example of gravitational lensing revealing dark matter is the Bullet cluster. In this collision between two galaxy clusters, the visible matter, primarily gas, was separated from the dark matter. The gas interacted and slowed down, but the dark matter detected through lensing passed through unaffected, highlighting the distinct roles they play. Gravitational lensing allows astronomers to trace dark matter's presence in the universe. By studying the distorted light from distant galaxies, scientists can map where dark matter is located, even though it doesn't emit or absorb light. These maps show that dark matter surrounds galaxies and clusters, forming massive halos. Lensing doesn't just show where dark matter is, it also helps confirm its abundance. The amount of dark matter inferred from gravitational lensing matches other observations, such as galaxy rotation curves, strengthening the case that dark matter makes up most of the universe's mass. Weak gravitational lensing, a more subtle form of the effect, offers further evidence. In this case, the distortions in light are less dramatic but still measurable. By analyzing these small distortions over large areas of the sky, scientists can study the distribution of dark matter on cosmic scales. Gravitational lensing is one of the few ways we can directly observe dark matter's effects. Since dark matter doesn't interact with light, we can't see it in the traditional sense, but its gravitational influence on light allows us to infer its presence. It's a direct window into the hidden side of the universe. The study of lensing has also revealed that dark matter doesn't clump together like ordinary matter. Instead, it forms vast, diffuse halos around galaxies and clusters, extending far beyond the visible boundaries. This suggests that dark matter behaves very differently from the matter we're familiar with. Lensing observations have even helped test alternative theories of gravity that attempt to explain the effects attributed to dark matter. However, these theories struggle to account for the lensing data, especially in cases like the bullet cluster, where dark matter appears separate from ordinary matter. This reinforces the idea that dark matter is a real, distinct component of the universe. Gravitational lensing also provides insights into the large-scale structure of the universe. Dark matter acts as the scaffolding for galaxy formation, and lensing reveals how this hidden framework is distributed across the cosmos. The patterns we observe through lensing match predictions based on the existence of dark matter. As technology improves, gravitational lensing is becoming an even more important tool for studying dark matter. With new telescopes and advanced data analysis techniques, astronomers are able to map dark matter more precisely than ever before. Each new observation adds to our understanding of this mysterious component of the universe. Clusters of galaxies are some of the largest structures in the universe, containing hundreds or even thousands of galaxies bound together by gravity. When scientists measure the mass of these clusters based on the visible galaxies, stars, and gas, they find a striking discrepancy. The visible matter isn't nearly enough to hold the cluster together. This phenomenon is known as the missing mass problem. The galaxies within these clusters are moving so fast that, without an additional source of gravity, they should have flown apart long ago. Yet, they remain bound, suggesting there's a large amount of invisible mass, providing the necessary gravitational pull. Much of this missing mass is believed to be dark matter. When astronomers calculate the total mass of a galaxy cluster using gravitational effects, such as how the galaxies move and how the cluster bends light through gravitational lensing, they find that dark matter makes up the majority of the mass. One of the most well-known examples is the Coma cluster, which Fritz Zwicky studied in the 1930s. Zwicky found that the mass of the visible matter in the cluster was far too small to account for the observed motions of the galaxies. This was one of the earliest clues that something invisible, dark matter, was influencing the cluster. Not only does dark matter provide the gravitational glue to hold galaxy clusters together, but it also influences how these clusters form. During the early stages of the universe, dark matter acted as a scaffold, helping regular matter collapse into the large-scale structures we see today. Without dark matter, clusters of galaxies might not exist in their current form. When we look at galaxy clusters in X-ray light, we can see vast clouds of hot gas that emit brightly. This gas makes up a large portion of the visible mass in clusters, but even when combined with the galaxies, it's still not enough to account for the total mass. Dark matter, though invisible, must be there in much larger quantities. The study of galaxy clusters also supports the idea that dark matter interacts very weakly, if at all, with ordinary matter. When clusters collide, the dark matter passes through undisturbed, while the visible matter, like gas, slows down and interacts. This separation between the two is observed in systems like the bullet cluster, offering direct evidence for dark matter. In clusters, dark matter isn't confined to the galaxies themselves. It extends beyond the visible galaxies, forming large halos that encompass the entire cluster. These halos dominate the mass and are responsible for the cluster's overall gravitational influence. The missing mass in clusters isn't just a small oversight, it represents the vast majority of the cluster's total mass. Around 85% of a galaxy cluster's mass is thought to be dark matter. This means that what we can see, galaxies and gas, only accounts for a small fraction of the true mass. Observing the motion of galaxies within clusters gives us further confirmation of dark matter's role. The speeds at which galaxies orbit the center of the cluster can only be explained by the presence of dark matter. Without it, the galaxies would not remain gravitationally bound. Clusters of galaxies are also used to study dark energy and the expansion of the universe. The distribution of mass, including dark matter, within these clusters helps scientists understand how structures in the universe evolve over time. The balance between dark matter and dark energy shapes the growth and future of these massive systems. Ultimately, galaxy clusters serve as natural laboratories for studying dark matter. Their size and complexity provide multiple ways to measure the unseen mass, and every method, from galaxy motions to gravitational lensing, points to the overwhelming presence of dark matter, filling in the gaps left by the missing mass problem. Technological advancements have dramatically improved our ability to study dark matter and dark energy. New generations of telescopes, both on Earth and in space, are providing unprecedented data on the large-scale structure of the universe. These tools allow us to probe deeper into the cosmos than ever before. One of the most significant advances is in the field of weak gravitational lensing. Instruments like the Dark Energy Survey use this technique to measure how dark matter warps the light from distant galaxies. By mapping these distortions, scientists can chart the distribution of dark matter across the universe. In space, the Hubble Space Telescope has been instrumental in studying dark matter through strong gravitational lensing. Its ability to capture high-resolution images of distant galaxies has helped researchers confirm that massive amounts of unseen matter are bending light. These observations provide further evidence for dark matter's existence. Ground-based observatories, such as the Large Synoptic Survey Telescope, are also contributing to our understanding. This telescope will capture vast amounts of data, scanning the entire sky every few nights. Its observations will help scientists track how dark energy influences the universe's expansion over time. Particle detectors are another key area of technological progress. Experiments like Xenon 1T and Lux Zeppelin aim to directly detect dark matter particles by capturing interactions between dark matter and regular matter. Though no particles have been confirmed yet, these detectors are becoming more sensitive with each new iteration. The Large Hadron Collider, LHC at CERN, is also searching for dark matter. By smashing particles together at incredibly high speeds, the LHC allows physicists to recreate the conditions of the early universe. If dark matter particles exist, they might be produced in these high-energy collisions. Another cutting-edge approach involves studying the cosmic microwave background, CMB. The Planck satellite provided a highly detailed map of this relic radiation from the early universe, offering insights into how dark matter and dark energy influence the universe's evolution. Future missions will build on this foundation. Radio astronomy is playing a growing role in the search for dark matter, particularly through projects like the Square Kilometre Array, SKA. This massive array of radio telescopes will be the largest in the world, enabling researchers to study the fine structure of galaxies and search for the faint signals that might reveal dark matter's presence. Advances in artificial intelligence and machine learning are also helping scientists sift through the massive datasets generated by these telescopes and experiments. These tools can identify patterns and anomalies that might otherwise be missed, accelerating the pace of discovery in cosmology. Technological advancements in space exploration have also led to the deployment of new missions, like the European Space Agency's Euclid satellite. Scheduled to launch soon, Euclid will map the geometry of the dark universe, helping to determine the properties of dark energy and dark matter with unprecedented precision. Quantum computing holds the potential to revolutionize how we simulate dark matter and dark energy. As this technology develops, it could allow scientists to model the complex interactions of particles and forces in ways that are impossible with classical computers. This may unlock new paths to understanding the fundamental nature of dark matter. Each of these advancements brings us closer to solving the mysteries of dark matter and dark energy. While we haven't yet found all the answers, the rapid development of new technologies ensures that we are moving steadily toward a deeper understanding of these elusive components of the universe. Type Ia supernovae have become one of the most important tools for measuring the expansion rate of the universe. These supernovae occur in binary star systems, where one of the stars is a white dwarf. When the white dwarf pulls in too much material from its companion, it reaches a critical mass and explodes in a bright, predictable burst of light. What makes Type Ia supernovae so valuable to cosmologists is their consistency. These explosions always reach the same peak brightness, allowing scientists to use them as standard candles. By comparing their observed brightness with how bright they should be, researchers can calculate their distance from Earth. In the late 1990s, astronomers studying Type Ia supernovae made a shocking discovery. They found that distant supernovae were dimmer than expected, which meant they were farther away than previously thought. This suggested that the expansion of the universe was accelerating, not slowing down. The discovery of this acceleration was completely unexpected and led to the introduction of dark energy into cosmological models. It was the Type Ia supernovae that provided the first direct evidence that something was pushing galaxies apart faster and faster. This changed our understanding of the universe's future. By studying more Type Ia supernovae, scientists have been able to measure the expansion rate of the universe with greater precision. This rate, known as the Hubble constant, describes how fast galaxies are moving away from each other. The data from these supernovae are critical in refining this value. The consistency of Type Ia supernovae allows them to be used across vast distances, providing a snapshot of the universe's expansion at different points in time. By observing supernovae from billions of years ago, astronomers can trace how the expansion rate has changed over cosmic history. These supernovae have helped confirm that dark energy makes up about 68% of the universe. Without the data from Type Ia supernovae, we wouldn't have such a clear understanding of how dominant dark energy is in driving the expansion of space. They offer a direct link between observation and theory. Type Ia supernovae don't just tell us about dark energy. They also help us understand the overall geometry of the universe. By comparing distances to the redshift of light from these supernovae, scientists can infer whether the universe is flat, open, or closed. Current data suggests the universe is flat, with dark energy influencing its fate. The precision of Type Ia supernova measurements continues to improve, thanks to advancements in telescope technology and data analysis. Large surveys, like the Dark Energy Survey and upcoming space missions, are collecting more supernovae data to refine our understanding of the universe's expansion. Despite their importance, there are still some uncertainties related to Type Ia supernovae. For instance, researchers are investigating whether all of these explosions are truly identical, or if small variations could affect the measurements. Understanding these nuances is crucial for accurate calculations of the universe's expansion. Type Ia supernovae also offer a glimpse into the distant future. If dark energy continues to drive the acceleration of the universe's expansion, galaxies will move farther and farther apart. Over time, the night sky will become darker, with fewer galaxies visible from Earth or any other vantage point. The role of Type Ia supernovae in cosmology cannot be overstated. They have provided some of the most compelling evidence for dark energy, helped measure the universe's expansion rate, and shaped our understanding of the cosmos on the largest scales. Without them, our picture of the universe would be far less complete. In 1998, two independent teams of scientists made a discovery that changed our understanding of the universe forever. They were studying distant Type Ia supernovae to measure how the universe's expansion had slowed down over time. But instead of finding a slowing expansion, they found the opposite. The teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, discovered that the universe's expansion was actually speeding up. This was a completely unexpected result, contradicting the assumption that gravity would eventually slow the expansion. This discovery provided the first direct evidence for the existence of dark energy. It showed that some unknown force was driving the accelerated expansion of the universe. The implications were profound, suggesting that dark energy makes up the majority of the universe's total energy content. The acceleration of the universe's expansion was a major surprise to the scientific community. Until then, most cosmologists assumed that the combined gravitational pull of all matter, including dark matter, would either slow the expansion or even reverse it, leading to a possible big crunch. The 1998 discovery forced scientists to rethink the fate of the universe. With dark energy now a dominant force, the future of the universe looked very different. Instead of slowing down, the universe would continue to expand at an accelerating rate, potentially leading to a cold, dark, and empty cosmos. This breakthrough led to the awarding of the 2011 Nobel Prize in Physics to Saul Perlmutter, Brian Schmidt, and Adam Rees. Their work transformed cosmology, bringing dark energy to the forefront of scientific inquiry. It opened new avenues of research and posed some of the biggest questions in modern physics. The discovery also prompted scientists to revise their models of the universe's composition. It was no longer just about visible matter and dark matter. Dark energy, an entirely new and mysterious component, had to be factored in, and it turned out to make up about 68% of the universe. The significance of the 1998 discovery cannot be overstated. It revealed that the universe is dominated by a force we don't yet understand. This forced scientists to confront the reality that most of the universe is made up of dark energy, which exerts a repulsive force, pushing space apart. Before this discovery, there were different models for the universe's ultimate fate, including scenarios where the universe would eventually stop expanding. The acceleration revealed by the supernova studies ruled out those models, showing that the universe would continue to expand indefinitely, driven by dark energy. The 1998 finding also had a profound impact on the study of cosmology and astrophysics. It shifted the focus from understanding only dark matter and the formation of galaxies to also investigating the nature of dark energy. This has led to a surge in experiments and observations aimed at unlocking the secrets of this mysterious force. With dark energy's discovery, we now know that our understanding of the universe is far from complete. It raises fundamental questions about the nature of space, time, and gravity. The 1998 discovery remains one of the most important scientific achievements of the 20th century, reshaping our view of the cosmos. This discovery continues to influence new theories in physics and cosmology. While we still don't know exactly what dark energy is, the 1998 breakthrough gave us a clear direction for future research. It marked the beginning of a new era in our quest to understand the universe. The cosmic microwave background, or CMB, is the faint glow of radiation left over from the Big Bang. It's the oldest light in the universe, dating back nearly 14 billion years, to a time when the universe was just 380,000 years old. This radiation gives us a snapshot of the early universe before stars and galaxies even formed. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB confirmed the Big Bang theory. Its uniformity across the sky provided strong evidence that the universe began in a hot, dense state and has been expanding ever since. But the CMB also contains tiny fluctuations that hold clues to the universe's composition. These fluctuations in the CMB represent slight variations in temperature, only a few millionths of a degree. They correspond to areas of slightly different densities in the early universe. Over billions of years, these small differences grew into the galaxies and clusters of galaxies we see today. The study of these temperature fluctuations has been key to understanding dark matter and dark energy. By analyzing the CMB, scientists can measure the density of matter and the geometry of the universe. This data helps determine how much of the universe is made up of dark matter, dark energy, and ordinary matter. One of the most important findings from the CMB is that the universe is flat. This means that the total amount of energy and matter in the universe is perfectly balanced. This balance requires the presence of dark energy to account for the missing portion of the universe's energy density. Observations of the CMB have also helped to refine the value of the Hubble constant, which describes the rate of the universe's expansion. By comparing CMB data with other methods, such as type Ia supernovae, scientists gain a clearer picture of how the expansion has changed over time. The Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided the most detailed maps of the CMB to date. These missions measured the temperature fluctuations with incredible precision, allowing scientists to make more accurate estimates of the universe's age, composition, and structure. From these measurements, we know that dark matter makes up about 27% of the universe and dark energy about 68%. The CMB data was crucial in confirming the existence of dark energy and in understanding how it influences the expansion of the universe. It shows us that dark energy began to dominate the universe several billion years ago. The CMB also tells us about the very early moments of the universe. It preserves the conditions from a time when the universe was still hot and dense, just after the Big Bang. This allows scientists to test models of the universe's origin and the rapid inflation that occurred in its first moments. Even though the CMB is uniform across the sky, its tiny fluctuations provide a wealth of information about the large-scale structure of the universe. These patterns reflect the seeds of cosmic structure that were later amplified by dark matter, helping form the galaxies we observe today. The detailed study of the CMB continues to reveal more about the universe's history. As new technologies allow for even finer measurements, the discovery of dark energy and the accelerating expansion of the universe has profound implications for its ultimate fate. If the expansion continues to accelerate, galaxies will move farther apart, and the universe will become increasingly isolated. Over billions of years, distant galaxies will slip beyond our observational reach. This process could lead to what's known as the Big Freeze. In this scenario, stars will eventually burn out, galaxies will drift away from each other, and the universe will grow colder and darker. Over time, the universe would continue to expand. But without the energy needed to form new stars, it would become a barren, frozen expanse. Another possibility is the Big Rip. If dark energy's influence grows stronger over time, the expansion could accelerate to the point where not just galaxies, but stars, planets, and even atoms are torn apart. This catastrophic end would occur if dark energy continues to increase in strength, driving the universe toward total disintegration. The current understanding suggests that dark energy is constant, meaning it won't change over time. But if it does evolve, the fate of the universe could change with it. Some theories suggest that dark energy could eventually weaken, slowing the expansion and leading to a different outcome, possibly a reversal of the expansion. One alternative to the Big Freeze or Big Rip is the Big Crunch. In this scenario, dark energy would reverse course, and the universe's expansion would slow, stop, and then contract. Over time, all matter would collapse back into a single point, possibly leading to another Big Bang. However, current observations suggest that dark energy will continue to dominate, making the Big Crunch unlikely. As dark energy drives the universe's expansion at an ever-increasing rate, it seems more likely that we are headed toward a universe that is cold, dark, and isolated. The fate of the universe also depends on the behavior of dark matter. While dark energy pushes galaxies apart, dark matter's gravity holds them together. The balance between these two forces will determine how structures like galaxies and clusters evolve over the next billions of years. If dark energy's influence remains steady, galaxy formation could slow, and the large-scale structure of the universe might begin to disintegrate. In the distant future, stars and galaxies might no longer be able to form, leaving behind only the remnants of what once was. These possibilities highlight the profound influence dark energy has on the future of the cosmos. The universe's fate is not just a question of distant speculation. It's being shaped right now by the mysterious forces that we are only beginning to understand. In addition to the physical changes, the expansion of the universe has implications for future observations. As space stretches, the light from distant galaxies will become redshifted to the point of invisibility, making it harder for future civilizations to study the cosmos. The eventual fate of the universe raises deep philosophical questions as well. What will happen to all the structures, stars, and galaxies that exist today? Will there be a final end? Or does the universe cycle through phases of expansion and collapse? While we don't have all the answers yet, the implications of dark energy's discovery have set the stage for a new era in cosmological research. Understanding how dark energy will evolve is key to unlocking the future of the universe and determining how it will all end. Galaxy rotation curves have provided some of the most compelling evidence for dark matter. When astronomers measure how stars and gas rotate around the center of a galaxy, they find something unexpected. The outer regions of galaxies rotate much faster than they should based on the visible matter alone. According to the laws of gravity, the stars far from the galactic center should move more slowly, similar to how planets in our solar system orbit the Sun. But observations show that the stars at the edges of galaxies are moving at nearly the same speed as those closer to the center. This discrepancy can't be explained by the mass of the stars, gas, and dust we can see. The visible matter simply doesn't provide enough gravitational pull to account for the high speeds. Something unseen must be contributing to the total mass of the galaxy. The flatness of galaxy rotation curves, where the speed of stars doesn't decrease with distance, points to the presence of a massive, invisible halo of dark matter. This dark matter surrounds galaxies, extending far beyond the visible edges, and provides the extra gravitational force needed to explain the rotation. Vera Rubin's work in the 1970s was critical in demonstrating this phenomenon. Her measurements of galaxy rotation curves showed that the discrepancy between visible matter and rotational speeds was consistent across different types of galaxies. This was one of the first pieces of strong evidence for dark matter's existence. The rotation curves of spiral galaxies are particularly revealing. In these galaxies, the stars in the disk rotate in a way that defies expectations based on the amount of visible mass. The dark matter halo is essential in explaining why these stars don't fly off into space as they orbit at such high speeds. Even in smaller galaxies, the same pattern is observed. The rotation speeds of stars are far too high to be explained by the mass we can detect. This suggests that dark matter is a universal component of galaxies, affecting their structure regardless of size or type. Computer simulations of galaxy formation that include dark matter are able to reproduce these rotation curves accurately. Without dark matter, the simulations fail to match what we observe in real galaxies. This has strengthened the case for dark matter as a key component in galactic dynamics. One of the most striking aspects of galaxy rotation curves is that they show the same behavior in both small, local galaxies and massive, distant ones. This uniformity suggests that dark matter is not just a local phenomenon, but something that permeates the entire universe. As technology has advanced, more precise measurements of rotation curves have been made, further confirming the presence of dark matter. Modern telescopes and instruments allow us to observe galaxies at greater distances, and in every case, the rotation curves remain flat where they should be declining. These rotation curves have also helped determine the distribution of dark matter within galaxies. Dark matter is most concentrated in the halo surrounding the galaxy, rather than in the central bulge or disk, where most of the visible matter resides. This distribution has important implications for understanding how galaxies form and evolve. The study of galaxy rotation curves continues to be a critical tool in cosmology. It provides direct, observable evidence of dark matter's gravitational influence, showing that the universe is filled with far more mass than we can see. Understanding these curves is key to unlocking the mysteries of dark matter and its role in shaping galaxies. Gravitational lensing occurs when light from a distant object is bent around a massive object between it and the observer. This bending is caused by the gravitational field of the intervening mass, which distorts and magnifies the light, similar to how a glass lens bends light. It's one of the clearest demonstrations of how mass warps space. This phenomenon was first predicted by Einstein's general theory of relativity. The more massive the object, the more pronounced the bending of light. In some cases, gravitational lensing can even create multiple images of a single distant object, or stretch its light into arcs and rings. Gravitational lensing is a powerful tool for studying dark matter because the amount of bending is directly related to the total mass of the lensing object. Often, the visible matter, like stars and gas, isn't enough to account for the degree of light bending observed. This points to the presence of significant amounts of unseen dark matter. One of the most famous examples of gravitational lensing is the Bullet cluster. In this system, two galaxy clusters have collided, separating the dark matter from the hot gas that can be seen in X-rays. The gravitational lensing maps show that most of the mass in the system is dark matter, which has passed through the collision unaffected. Strong gravitational lensing creates dramatic effects, like multiple images of distant galaxies or the rare and beautiful Einstein rings. These phenomena occur when the alignment between the observer, the lens, and the background object is just right, producing nearly perfect circular distortions of light. Even when the lensing effects are weaker, known as weak gravitational lensing, the slight distortions in the shapes of distant galaxies can still be measured. By studying these small distortions across large areas of the sky, scientists can map the distribution of dark matter on cosmic scales. Gravitational lensing doesn't just show where dark matter is, it also reveals its distribution. Dark matter tends to form large halos around galaxies and clusters, and lensing helps to map these invisible structures. These dark matter halos are much more massive than the visible parts of the galaxies themselves. One of the key aspects of gravitational lensing is that it's not limited to studying individual galaxies. Lensing can be used to explore the large-scale structure of the universe, helping scientists understand how dark matter clumps together and how it influences the formation of cosmic structures. Lensing also offers a way to study objects that would otherwise be too distant or faint to observe. When the light from a distant galaxy is magnified by a foreground cluster, it allows astronomers to study galaxies from the early universe in unprecedented detail. This has provided valuable insights into how galaxies evolve over time. By observing lensing effects, scientists can also test alternative theories of gravity. Some modified theories attempt to explain the universe's structure without dark matter, but the lensing data generally supports the existence of large amounts of invisible mass. These observations reinforce the idea that dark matter is a fundamental part of the cosmos. The precision of gravitational lensing measurements has improved with new technologies, including space telescopes like Hubble and future missions like the James Webb Space Telescope. These instruments provide sharper images, allowing for more detailed studies of lensing effects and better mapping of dark matter. Gravitational lensing is one of the most direct ways we can study dark matter, offering a glimpse into the otherwise invisible side of the universe. As we continue to refine our techniques and gather more data, lensing will remain a key tool in unraveling the mysteries of dark matter and the structure of the cosmos. The formation of structure in the universe, from galaxies to galaxy clusters, is deeply influenced by dark matter. After the Big Bang, the universe was mostly a hot, uniform sea of particles. Over time, tiny fluctuations in density allowed regions of higher mass to grow under the influence of gravity. Dark matter played a crucial role in this process. Because it doesn't interact with light or radiation, dark matter could begin clumping together even when the universe was still filled with hot plasma. These clumps of dark matter acted as gravitational wells, pulling in ordinary matter. Without dark matter, the formation of galaxies and large-scale structures would have taken much longer, if it happened at all. The gravitational pull of dark matter accelerated the process, allowing ordinary matter to collapse into stars and galaxies relatively quickly in cosmic terms. As dark matter clumped together, it formed the cosmic web, a vast network of filaments and voids that stretches across the universe. The galaxies we see today are located along these filaments, where dark matter is most densely concentrated. This web-like structure defines the large-scale organization of the cosmos. Simulations of the universe that include dark matter show how essential it is for structure formation. Without it, the universe would be much smoother, with fewer galaxies and galaxy clusters. Dark matter provides the gravitational scaffolding necessary for these structures to form. The first stars and galaxies formed in regions where dark matter was particularly dense. These areas, often referred to as dark matter halos, provided the gravitational pull needed to gather gas and dust, eventually leading to the ignition of the first stars. These early structures later merged to form the galaxies we see today. As galaxies formed, they began to cluster together under the influence of gravity, again guided by dark matter. Over time, small galaxies merged to form larger ones, and galaxy clusters grew around dense knots of dark matter. These clusters, connected by dark matter filaments, form the largest structures in the universe. Dark matter also helped prevent early structures from being torn apart by the rapid expansion of the universe. Its gravitational pull was strong enough to counteract the expansion in localized regions, allowing galaxies and clusters to remain bound together while the universe continued to grow. The scale of structure formation is vast, with galaxy clusters stretching millions of light-years across. These clusters are held together by massive halos of dark matter, which extend far beyond the visible edges of galaxies. The dark matter halo acts as a binding force, stabilizing these enormous structures. Observations of the cosmic microwave background provide a snapshot of the universe before structure formation began. The tiny fluctuations in this radiation are the seeds of the large-scale structure we see today, and they align with what we expect from dark matter's influence on the early universe. As galaxies formed and evolved, dark matter continued to shape their growth. It helps explain why galaxies rotate as fast as they do, why they cluster in certain ways, and why the universe has its web-like structure. Dark matter is fundamental to the entire process of cosmic evolution. The study of structure formation is ongoing, and new observations and simulations continue to refine our understanding of how dark matter and ordinary matter interact. As we uncover more about this process, we get closer to answering some of the most profound questions about the nature of the universe. Hot and cold dark matter are two different types of dark matter, distinguished by their speeds, and how they influence the formation of cosmic structures. Hot dark matter consists of fast-moving particles, while cold dark matter is made up of slow-moving, massive particles. Hot dark matter, such as neutrinos, moves close to the speed of light. Because of this high velocity, it doesn't easily clump together. In the early universe, hot dark matter would have smoothed out any density fluctuations, preventing the formation of small-scale structures like galaxies. Cold dark matter, on the other hand, moves much more slowly. It clumps together more easily, forming the gravitational wells that eventually pulled in gas and dust to create stars and galaxies. This makes cold dark matter far more effective at forming the large-scale structures we observe today. The idea of hot dark matter fell out of favor as it became clear that it couldn't account for the small-scale structure of the universe. If the universe were dominated by hot dark matter, we wouldn't see the galaxies, clusters, and cosmic web that we do. Instead, everything would be more uniform. Cold dark matter has become the leading theory because it explains how galaxies could form so early in the universe's history. By allowing small clumps of matter to grow over time, cold dark matter provides a natural explanation for the large structures that exist in the cosmos. Simulations of the universe that include cold dark matter match observational data, especially regarding galaxy formation and the cosmic web. Without cold dark matter, these simulations fail to produce the universe we see today. This further supports the idea that cold dark matter plays a dominant role. Warm dark matter is another concept, sitting between hot and cold dark matter in terms of speed. It moves faster than cold dark matter, but slower than hot dark matter. Some scientists explore warm dark matter as a possibility, but cold dark matter remains the most widely accepted model. The distinction between hot and cold dark matter is crucial for understanding the evolution of the universe. While both forms of dark matter affect structure formation, only cold dark matter can explain how small structures like galaxies came together as quickly as they did after the Big Bang. Hot dark matter, while no longer seen as the primary driver of structure formation, still plays a role in cosmology. Neutrinos, for example, are a type of hot dark matter, and their properties can affect the overall behavior of the universe, though they don't dominate the process of galaxy formation. The concept of cold dark matter has been successful in explaining many observations, including the distribution of galaxies and the flatness of galaxy rotation curves. It also fits well with the data from the cosmic microwave background and large-scale structure surveys, reinforcing its place in cosmological models. Cold dark matter particles are likely massive and interact very weakly with ordinary matter, making them difficult to detect directly. Despite their elusive nature, their gravitational effects are seen everywhere in the universe, from individual galaxies to galaxy clusters and the cosmic web. The debate between hot and cold dark matter has shaped much of modern cosmology. While cold dark matter is now the dominant theory, understanding both concepts helps scientists refine their models of how the universe evolved and how dark matter influences its structure. The bullet cluster experiment provided some of the clearest evidence for the existence of dark matter. This galaxy cluster collision, observed in 2006, showed a separation between the visible matter and the gravitational effects of mass, revealing dark matter in action. It became a key piece of observational evidence supporting the dark matter theory. In the bullet cluster, two galaxy clusters collided at incredibly high speeds. During the collision, the hot gas from each cluster interacted, slowing down and emitting X-rays. This gas is the most visible form of matter in clusters, but it accounts for only a small portion of the total mass. What made the bullet cluster so significant was that, while the visible matter in the form of gas slowed down and remained at the center, the gravitational lensing data showed that most of the mass had passed through unaffected. This suggested that an invisible form of matter, later identified as dark matter, had continued moving through the collision without interacting. Gravitational lensing allowed scientists to map the total mass of the bullet cluster. By measuring how the light from distant galaxies was bent by the mass of the cluster, researchers could create a detailed map showing where most of the mass was located. The results showed that the majority of the mass was not where the visible gas was. The dark matter in the bullet cluster did not interact with the ordinary matter in the same way that the gas did. This non-interaction is a hallmark of dark matter, which only interacts through gravity. The bullet cluster experiment provided direct evidence that dark matter exists separately from normal matter and behaves differently during cosmic events. One of the reasons the bullet cluster is so compelling is that it rules out many alternative theories that try to explain the effects attributed to dark matter. Modified gravity theories, for instance, struggle to explain the clear separation of mass and visible matter in the bullet cluster. The lensing data clearly pointed to the presence of a massive unseen component. The bullet cluster experiment also helped to confirm the idea that dark matter forms large halos around galaxies and galaxy clusters. In this case, the dark matter halos from both clusters continued moving through the collision while the ordinary matter was left behind. This helped to illustrate how dark matter behaves on cosmic scales. The fact that dark matter didn't slow down or interact with the gas shows that it's not made of the same particles as ordinary matter. While the gas particles interacted through electromagnetic forces, the dark matter particles only influenced their surroundings through gravity, making them invisible to our usual detection methods. This separation between dark matter and visible matter in the bullet cluster provides a kind of cosmic laboratory for studying how dark matter works. By observing such collisions, scientists can gather more data on how dark matter moves, how much mass it carries, and how it affects the overall structure of the universe. The bullet cluster isn't the only example of such a phenomenon, but it's one of the most well-known and studied. Similar galaxy cluster collisions have been observed, reinforcing the conclusions drawn from the bullet cluster. Each new observation adds more evidence to the case for dark matter. This experiment also gave scientists a way to test their models of the universe. By comparing simulations of galaxy cluster collisions with the bullet cluster data, they can refine their understanding of dark matter and its role in the universe. The more we study these cosmic events, the clearer the picture of dark matter becomes. The bullet cluster remains a pivotal observation in the quest to understand dark matter. It provides direct, observable evidence of dark matter's existence and behavior, helping to solidify its place as a critical component in our understanding of the cosmos. Supernova observations have become essential in understanding the expansion of the universe and the presence of dark energy. Type Ia supernova, in particular, are used as standard candles to measure vast cosmic distances. These supernovae occur when a white dwarf star in a binary system accumulates enough material from its companion star to trigger a massive explosion. Because type Ia supernovae have a consistent peak brightness, astronomers can calculate how far away they are by comparing their observed brightness with their intrinsic luminosity. This makes them reliable tools for measuring the rate at which the universe is expanding. In the late 1990s, astronomers studying distant supernovae made a groundbreaking discovery. They found that these supernovae were dimmer than expected, indicating they were farther away than predicted by models of a decelerating universe. This provided the first direct evidence that the universe's expansion was accelerating. This unexpected acceleration led to the discovery of dark energy, the mysterious force driving the universe apart at an increasing rate. The supernova data suggested that dark energy makes up roughly 68% of the universe, vastly outnumbering dark matter and ordinary matter combined. By observing supernovae at different distances, astronomers can trace the expansion history of the universe. This allows them to see how the expansion rate has changed over time and provides clues about the nature of dark energy. The more supernovae we observe, the more detailed our understanding of the universe's expansion becomes. Supernova observations have also helped refine the value of the Hubble constant, which describes how fast the universe is expanding. By measuring both nearby and distant supernova, astronomers can improve the accuracy of this fundamental constant, which is critical for understanding the universe's overall dynamics. These observations provide crucial data for testing cosmological models. The behavior of supernovae at different redshifts helps scientists compare theories about the universe's expansion, from the influence of dark energy to alternative models of gravity. The consistent results from supernova observations strongly support the existence of dark energy. One of the challenges in supernova observations is accounting for potential variations in the explosions themselves. Although type Ia supernovae are remarkably uniform, small differences in their environments or progenitor systems could affect their brightness. Astronomers work to refine their models to account for these variables and improve the precision of distance measurements. Ongoing supernova surveys, such as the Dark Energy Survey and the Supernova Legacy Survey, continue to gather data on these distant explosions. With new telescopes and more advanced techniques, astronomers are now able to discover and study supernova at even greater distances, extending our understanding of the universe's early history. Supernova observations don't just inform us about dark energy. They also shed light on the overall structure and evolution of the universe. By combining supernova data with observations from other cosmic phenomena, scientists can build a more complete picture of how the universe has changed over billions of years. The study of supernovae is far from over. Future missions like the upcoming Vera Rubin Observatory are expected to detect thousands more supernovae, providing an even larger dataset to analyze. These discoveries will help scientists continue to refine their models of dark energy and cosmic expansion. In the end, supernova observations offer a unique window into the workings of the universe. They have revolutionized our understanding of cosmic expansion and dark energy, and they continue to be one of the most important tools in cosmology for unlocking the mysteries of the universe's fate. Cosmic microwave background measurements have been crucial in shaping our understanding of the early universe and the forces that govern it. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of what it looked like 380,000 years after its birth. By studying the tiny fluctuations in the temperature of the CMB, scientists can learn about the distribution of matter and energy at that time. These fluctuations are imprints of the seeds of cosmic structure, showing how regions of higher density eventually grew into galaxies and clusters. One of the most important findings from CMB measurements is the confirmation that the universe is flat. This means the geometry of space-time is not curved on large scales, and this flatness is only possible if dark energy makes up a significant portion of the universe's total energy density. The Wilkinson Microwave Anisotropy Probe, WIMP, was one of the first missions to provide a detailed map of these fluctuations. Its data revealed precise information about the composition of the universe, confirming that only a small fraction is made up of ordinary matter, while the rest is dark matter and dark energy. Following WIMP, the Planck satellite took even more detailed measurements of the CMB. The Planck data allowed scientists to refine their estimates of the age of the universe, its expansion rate, and the proportions of dark matter and dark energy. This made the CMB one of the most powerful tools for understanding cosmology. CMB measurements also help to determine the Hubble constant, the rate of expansion of the universe. By comparing these measurements with other methods, such as supernova observations, scientists can gain a clearer picture of how the expansion rate has evolved over time. These measurements have revealed that dark energy became dominant several billion years ago. Before that, the universe's expansion was primarily influenced by dark matter and ordinary matter. The CMB gives us a window into the time before dark energy took control, helping us understand how the universe transitioned to its current state. The detailed structure of the CMB fluctuations also provides insights into the formation of large-scale cosmic structures. By analyzing the patterns of these fluctuations, scientists can test theories about how dark matter clumped together in the early universe and how galaxies and clusters formed. CMB measurements are also used to test different models of dark energy. By comparing the observed data with theoretical predictions, scientists can rule out certain models and narrow down the possible explanations for dark energy's role in cosmic expansion. This helps refine our understanding of dark energy's properties. In addition to dark energy and dark matter, the CMB measurements provide clues about the universe's inflationary period, a time of rapid expansion just after the Big Bang. Studying the CMB helps test inflationary models, offering insight into the physics of the very early universe. Future missions like the CMB S4 project aim to provide even more precise measurements. These missions will study the polarization of the CMB, looking for signs of primordial gravitational waves and other subtle signals that could unlock new information about the universe's earliest moments. Cosmic microwave background measurements have become a cornerstone of modern cosmology. They give us a direct view of the universe's infancy and provide the framework for understanding how dark matter and dark energy have shaped the cosmos over billions of years. The large-scale structure of the universe is the vast web-like arrangement of galaxies, galaxy clusters, and dark matter that fills the cosmos. Over billions of years, gravity has pulled matter into these intricate patterns, forming massive filaments and vast voids between them. This cosmic web is one of the universe's most striking features. At the heart of this structure are galaxy clusters, the largest gravitationally bound objects in the universe. These clusters, connected by filaments of dark matter, form the nodes of the cosmic web. Between these filaments lie enormous voids, regions of space that contain very few galaxies. The formation of this large-scale structure was driven by the initial fluctuations in density that we observe in the cosmic microwave background. Over time, these tiny differences in density grew under the influence of dark matter, eventually leading to the formation of galaxies, clusters, and the cosmic web. Dark matter plays a key role in shaping this structure. Because it doesn't interact with light, dark matter can begin clumping together early in the universe's history, long before ordinary matter cools enough to form stars and galaxies. Its gravitational pull draws in regular matter, guiding the formation of the structures we see today. Simulations of the universe, like the Millennium simulation, show how dark matter forms the backbone of the large-scale structure. These simulations use the known laws of physics to model the growth of dark matter over billions of years. When ordinary matter follows the dark matter's distribution, the result is a universe that looks remarkably like the one we observe. Galaxies are not randomly distributed across the universe, but tend to cluster along the dark matter filaments. These filaments can stretch for hundreds of millions of light years, forming long chains of galaxies that connect massive clusters. This network of filaments and clusters is what defines the cosmic web. In between the filaments are the voids, some of the emptiest regions in the universe. These voids can be hundreds of millions of light years across, containing very little matter. The contrast between the dense filaments and the vast voids highlights the dynamic nature of the universe's large-scale structure. Studying the large-scale structure helps scientists understand how the universe has evolved over time. By mapping the distribution of galaxies and dark matter, astronomers can trace the history of structure formation, providing insights into the behavior of dark energy and dark matter. The Sloan Digital Sky Survey has played a major role in mapping the large-scale structure of the universe. By cataloging the positions of millions of galaxies, it has revealed the detailed web-like arrangement of matter on scales never seen before, offering a clearer picture of how the universe is organized. As we observe more distant galaxies, we're actually looking back in time, seeing the large-scale structure at earlier stages of its evolution. These observations allow astronomers to study how the cosmic web has grown and changed over billions of years, shedding light on the universe's expansion and the influence of dark energy. The large-scale structure also provides a powerful test for cosmological models. The distribution of galaxies and dark matter can be compared to predictions from simulations and theoretical models. Any discrepancies between observations and theory could point to new physics or a deeper understanding of dark matter and dark energy. Future surveys, like those from the Euclid and the Vera Rubin Observatory, will map the large-scale structure in even greater detail. These next-generation surveys will allow scientists to explore how dark energy influences the growth of the cosmic web and further refine our understanding of the universe's evolution. Baryon acoustic oscillations, or BAO, are regular, periodic fluctuations in the density of visible matter in the universe. These ripples originated in the early universe, when sound waves moved through the hot plasma that filled space before atoms could form. When the universe cooled and these sound waves froze in place, they left behind an imprint on the large-scale structure of the cosmos. These ripples are crucial for understanding the distribution of galaxies across the universe. The BAO serve as a cosmic ruler, allowing astronomers to measure the distances between galaxies. By studying these patterns, scientists can track how structures in the universe have evolved over billions of years. BAO are directly linked to the cosmic microwave background. The same sound waves that created the fluctuations in the CMB also caused the matter in the universe to clump together in these periodic waves. These ripples then influenced the formation of galaxies and clusters, shaping the large-scale structure we see today. The scale of these oscillations is incredibly vast, about 500 million light-years across. This makes them an ideal tool for measuring cosmic distances on a very large scale. By comparing the observed BAO in galaxy surveys with theoretical predictions, scientists can refine their understanding of the universe's expansion rate. One of the key contributions of BAO measurements is their role in determining the Hubble constant, the rate at which the universe is expanding. By using BAO as a standard ruler, astronomers can more accurately calculate how fast galaxies are moving away from each other, providing insights into dark energy's influence. The Sloan Digital Sky Survey has been instrumental in detecting BAO in the large-scale distribution of galaxies. Its data provided some of the first direct measurements of these oscillations in the universe's matter, confirming their existence and offering a powerful tool for cosmological research. BAO also offer a way to study the nature of dark energy. As the universe expands, the scale of BAO should change in predictable ways. By measuring this change over time, scientists can gain insights into how dark energy is driving the accelerated expansion of the universe. The periodic nature of BAO helps scientists understand how galaxies and galaxy clusters are distributed. Even though dark matter plays a dominant role in structure formation, baryonic matter, or ordinary matter, was also influenced by these early oscillations, leading to the clustering patterns we observe today. Because BAO are linked to the early universe, they serve as a bridge between the physics of the Big Bang and the large-scale structure of the modern universe. This connection makes them one of the most important tools for studying the universe's history, from its earliest moments to its current state. Future surveys like those from the Dark Energy Spectroscopic Instrument, DESI, aim to measure BAO across a larger volume of the universe. These surveys will provide more precise data, allowing scientists to map the distribution of galaxies with even greater accuracy and study how dark energy has shaped the cosmos over time. BAO provide a way to cross-check other methods of measuring the universe's expansion, such as supernova observations and gravitational lensing. By combining BAO data with these other techniques, astronomers can build a more complete picture of the universe's behavior and its ultimate fate. As we continue to refine our measurements of BAO, they will remain a key tool in cosmology. They offer a window into the universe's early conditions and its large-scale structure, helping us understand the forces shaping the cosmos, including dark matter and dark energy. Galaxy clusters provide some of the most compelling evidence for the presence of dark matter and the influence of dark energy. These massive structures, containing hundreds or thousands of galaxies, are bound together by gravity, but the visible matter alone is not enough to explain their stability. The additional mass, which we cannot see, is believed to be dark matter. Observations of galaxy clusters reveal that dark matter plays a crucial role in holding these clusters together. Without it, the galaxies within the clusters would move too quickly to remain bound by the gravity of ordinary matter alone. This discrepancy has been confirmed through detailed measurements of galaxy velocities within clusters. Gravitational lensing, where the mass of a galaxy cluster bends the light of more distant objects, further confirms the existence of dark matter. The amount of bending observed often far exceeds what would be expected from the visible matter alone, indicating the presence of a vast amount of unseen mass. X-ray observations of galaxy clusters also provide critical insights. The hot gas in clusters emits X-rays, and this gas makes up most of the visible matter in clusters. However, even when accounting for this gas, the total mass falls short. Dark matter is necessary to explain the additional gravitational pull that binds the gas and galaxies together. Galaxy clusters are also valuable for studying dark energy. As the universe expands, dark energy drives clusters further apart from each other. By observing how clusters move and spread across space, scientists can infer the strength and behavior of dark energy over time. The largest galaxy clusters also offer a glimpse into the early universe. The most distant clusters, observed billions of light-years away, formed when the universe was much younger. Studying these clusters helps scientists understand how structure formation has evolved over cosmic history, guided by both dark matter and dark energy. Another important observation comes from the Sunyaev-Zeldovich effect, where the cosmic microwave background radiation interacts with the hot gas in galaxy clusters. This effect allows scientists to study clusters at great distances and provides another method for measuring their total mass, including dark matter. By mapping the distribution of galaxy clusters across the sky, astronomers can trace the large-scale structure of the universe. Clusters form at the densest points of the cosmic web, and their distribution helps to test models of dark matter and the effects of dark energy on the growth of cosmic structures. Clusters also serve as natural laboratories for testing theories of modified gravity. Some theories attempt to explain dark matter effects through changes in our understanding of gravity itself. However, the behavior of galaxy clusters, particularly in collisions like the bullet cluster, strongly supports the presence of dark matter rather than a modification of gravity. The study of clusters helps to refine our understanding of the universe's total mass-energy content. Observations show that dark matter makes up roughly 85% of the mass in clusters, with the rest being visible matter. This breakdown aligns closely with the overall composition of the universe, where dark matter dominates over ordinary matter. The movement of galaxies within clusters also provides insights into the balance between dark matter and dark energy. As clusters form and grow, dark matter pulls galaxies together, while dark energy works to push them apart on larger scales. Observing these interactions helps scientists model the future evolution of the universe. As technology improves, observations of galaxy clusters will become even more detailed, offering clearer insights into dark matter, dark energy, and the forces that shape the universe. These observations continue to be a cornerstone of modern cosmology, helping to answer some of the most fundamental questions about the universe's composition and fate. Weakly interacting massive particles, or WIMPs, are one of the leading candidates for dark matter. These hypothetical particles are thought to have mass, but interact only through the weak nuclear force and gravity, making them extremely difficult to detect. Despite their elusive nature, WIMPs could account for the vast majority of dark matter in the universe. The idea behind WIMPs comes from particle physics. These particles would have been created in large quantities during the early universe, left over from the high-energy conditions just after the Big Bang. Since they don't interact with light, WIMPs would remain invisible, but their mass would still exert gravitational influence. WIMPs are considered cold dark matter, meaning they move slowly compared to the speed of light. This slow movement allows them to clump together, forming the dark matter halos that surround galaxies and galaxy clusters. These halos provide the gravitational pull that helps hold galaxies together, even as they rotate at high speeds. One of the reasons WIMPs are a popular dark matter candidate is that they fit neatly into theories beyond the standard model of particle physics, particularly supersymmetry. In these models, WIMPs could be the lightest stable particle, making them a natural explanation for dark matter. Scientists have developed several ways to try and detect WIMPs, even though they rarely interact with normal matter. One approach is through direct detection, where extremely sensitive detectors are placed deep underground to shield them from cosmic rays. These detectors are designed to catch the occasional interaction between a WIMP and a regular particle. Another method of detecting WIMPs is through indirect detection, looking for the products of WIMP annihilation. If WIMPs collide and destroy each other, they might produce gamma rays or other particles that could be detected by space-based telescopes like Fermi. These signals would point to regions of high dark matter density, such as the centers of galaxies. The Large Hadron Collider, LHC, is also being used to search for WIMPs. By smashing protons together at high energies, scientists hope to create WIMPs in the lab. If they do, the WIMPs would escape the detector without interacting, leaving behind missing energy, an indirect sign that they were produced. Despite many experiments, WIMPs have not yet been detected. This has led some scientists to reconsider other dark matter candidates, such as axions or sterile neutrinos. However, the search for WIMPs continues, as they remain a compelling explanation for dark matter based on current physics models. One of the key challenges in detecting WIMPs is their incredibly weak interaction with ordinary matter. These particles could pass through the Earth, or even a detector, without ever hitting anything. This makes finding them a matter of patience and precision, using highly sophisticated technology to catch even the smallest interaction. The discovery of WIMPs would revolutionize our understanding of both dark matter and particle physics. It would provide a direct link between the mysterious dark matter that shapes galaxies and the fundamental particles that make up the universe, bridging the gap between cosmology and particle physics. If WIMPs are found, it would confirm that dark matter is made of particles that fit into our existing theories of physics, offering a long-sought solution to one of the universe's biggest mysteries. But even if WIMPs remain undetected, their search is helping to refine our understanding of dark matter and pushing the boundaries of what we know about the universe. In the coming years, new experiments and more sensitive detectors may finally reveal whether WIMPs are the elusive particles that make up dark matter. Until then, WIMPs remain one of the most promising and intriguing candidates for explaining the unseen mass that shapes the cosmos. Axions are another leading candidate for dark matter, offering a very different explanation than WIMPs. These hypothetical particles are extremely light, much lighter than most other particles we know of, and they don't carry any electric charge. Despite their low mass, they could exist in enormous quantities, making up the bulk of dark matter. The idea of axions first arose as a solution to a problem in quantum chromodynamics, the theory that describes how quarks and gluons interact. Axions were proposed to explain why certain properties of these interactions don't violate symmetry, something physicists refer to as the strong CP problem. If axions exist, they would be cold dark matter, like WIMPs, meaning they would move slowly and could clump together in halos around galaxies. Unlike WIMPs, however, axions are thought to be very light and could behave more like a field spread throughout space than individual particles. Detecting axions would require very different techniques from those used to find WIMPs. One method involves looking for the conversion of axions into photons or light particles in the presence of strong magnetic fields. Experiments like ADMX are designed to catch these rare interactions by using powerful magnets and extremely sensitive detectors. Another feature of axions is that they could affect the behavior of light passing through magnetic fields, causing a slight change in polarization. This effect might be observed in certain astrophysical environments, giving astronomers another potential way to detect axions indirectly. In addition to axions, there are other hypothetical particles that might explain dark matter. One such candidate is the sterile neutrino. Unlike regular neutrinos, which are known to interact via the weak nuclear force, sterile neutrinos would interact only through gravity, making them an ideal dark matter candidate. Sterile neutrinos would be much heavier than normal neutrinos and would not interact with ordinary matter in the same way. Their presence would be felt only through their gravitational influence, and they might decay into lighter particles such as X-rays that could be detected by space telescopes. Another exotic dark matter candidate is the dark photon. In some extensions of the Standard Model, the idea of a dark sector emerges, where dark matter particles could interact with each other through a force mediated by dark photons. These particles wouldn't interact with ordinary light, but could carry a similar role in dark matter interactions. The dark photon is interesting because it offers a way for dark matter to interact with itself, potentially explaining certain observations where dark matter doesn't behave exactly as expected. For example, dark matter might clump together differently in some galaxies, and the dark photon could help explain these anomalies. The search for these hypothetical particles is ongoing, with experiments designed to look for small effects that might reveal their existence. Whether through particle physics experiments or astronomical observations, these searches are pushing the boundaries of what we know about the universe. While WIMPs remain a dominant theory, the discovery of axions, sterile neutrinos, or dark photons would open entirely new avenues of understanding. Each of these particles offers a different explanation for dark matter and would dramatically reshape our understanding of physics if detected. As we continue exploring these possibilities, the discovery of any of these particles would not only solve the dark matter mystery, but also provide deep insights into the fundamental forces that govern the universe. Supersymmetry is a theoretical framework that extends the Standard Model of particle physics by proposing a symmetry between two types of particles, fermions and bosons. In this theory, Every known particle has a heavier superpartner. These superpartners, if they exist, could provide a natural candidate for dark matter. One of the most promising supersymmetric candidates for dark matter is the neutralino. Neutralinos are stable, electrically neutral, and interact only weakly with ordinary matter, making them an excellent match for the properties we expect dark matter to have. If neutralinos exist, they could account for much of the unseen mass in the universe. In supersymmetry, neutralinos would be the lightest supersymmetric particle, or LSP. Because they are stable and don't decay into other particles, these neutralinos could have been produced in large quantities during the early universe and survived to the present day, forming the dark matter halos around galaxies. Supersymmetry also helps solve several problems in particle physics. It provides a solution to the hierarchy problem, which deals with why the Higgs boson has a relatively low mass compared to other fundamental forces. The existence of supersymmetric particles could stabilize the Higgs boson's mass and make the overall theory of particle physics more consistent. The search for supersymmetric particles, including those that could be dark matter, is one of the main goals of the Large Hadron Collider, LHC. Scientists hope that high-energy collisions at the LHC might produce these particles, allowing them to detect dark matter indirectly by observing missing energy and particle interactions. If supersymmetry is correct, it could also unify the forces of nature. In many versions of the theory, supersymmetry links the strong, weak, and electromagnetic forces at high-energy scales, pointing to a grand unified theory. Discovering a supersymmetric dark matter particle would provide key evidence for these unification ideas. One of the reasons supersymmetry is so appealing as a dark matter theory is that it naturally predicts a stable, weakly interacting particle that fits well with our current understanding of dark matter. This makes it an attractive candidate, although no supersymmetric particles have been discovered yet. However, the lack of direct evidence for supersymmetry has led some scientists to explore other possibilities. While supersymmetry remains a leading theory, alternative models such as axions or sterile neutrinos are being considered as potential dark matter candidates. This reflects the ongoing challenge of solving the dark matter mystery. Despite the challenges, supersymmetry still offers a compelling explanation for dark matter. If neutralinos or other supersymmetric particles are discovered, it would not only solve the dark matter problem, but also revolutionize our understanding of fundamental physics, opening the door to a new era of particle science. The detection of supersymmetric dark matter would also help explain the large-scale structure of the universe. These particles could provide the missing mass needed to hold galaxies and clusters together, while their weak interactions would explain why they have been so difficult to detect directly. Supersymmetry is also flexible enough to accommodate different types of dark matter. Depending on the details of the theory, different supersymmetric particles could make up dark matter in various forms, providing a versatile framework for understanding the unseen mass in the universe. As experiments at the LHC and other facilities continue to probe the nature of dark matter, the discovery of supersymmetric particles would be a major breakthrough. It would confirm long-standing theoretical predictions and provide a clear link between the mysterious dark matter and the deeper structure of the universe. Supersymmetry is a theoretical framework that extends the standard model of particle physics by proposing a symmetry between two types of particles, fermions and bosons. In this theory, every known particle has a heavier superpartner. These superpartners, if they exist, could provide a natural candidate for dark matter. One of the most promising supersymmetric candidates for dark matter is the neutralino. Neutralinos are stable, electrically neutral, and interact only weakly with ordinary matter, making them an excellent match for the properties we expect dark matter to have. If neutralinos exist, they could account for much of the unseen mass in the universe. In supersymmetry, neutralinos would be the lightest supersymmetric particle, or LSP. Because they are stable and don't decay into other particles, these neutralinos could have been produced in large quantities during the early universe and survived to the present day, forming the dark matter halos around galaxies. Supersymmetry also helps solve several problems in particle physics. It provides a solution to the hierarchy problem, which deals with why the Higgs boson has a relatively low mass compared to other fundamental forces. The existence of supersymmetric particles could stabilize the Higgs boson's mass and make the overall theory of particle physics more consistent. The search for supersymmetric particles, including those that could be dark matter, is one of the main goals of the Large Hadron Collider, LHC. Scientists hope that high-energy collisions at the LHC might produce these particles, allowing them to detect dark matter indirectly by observing missing energy in particle interactions. If supersymmetry is correct, it could also unify the forces of nature. In many versions of the theory, supersymmetry links the strong, weak, and electromagnetic forces at high energy scales, pointing to a grand unified theory. Discovering a supersymmetric dark matter particle would provide key evidence for these unification ideas. One of the reasons supersymmetry is so appealing as a dark matter theory is that it naturally predicts a stable, weakly interacting particle that fits well with our current understanding of dark matter. This makes it an attractive candidate, although no supersymmetric particles have been discovered yet. However, the lack of direct evidence for supersymmetry has led some scientists to explore other possibilities. While supersymmetry remains a leading theory, alternative models such as axions or sterile neutrinos are being considered as potential dark matter candidates. This reflects the ongoing challenge of solving the dark matter mystery. Despite the challenges, supersymmetry still offers a compelling explanation for dark matter. If neutralinos or other supersymmetric particles are discovered, it would not only solve the dark matter problem, but also revolutionize our understanding of fundamental physics, opening the door to a new era of particle science. The detection of supersymmetric dark matter would also help explain the large-scale structure of the universe. These particles could provide the missing mass needed to hold galaxies and clusters together, while their weak interactions would explain why they have been so difficult to detect directly. Supersymmetry is also flexible enough to accommodate different types of dark matter. Depending on the details of the theory, different supersymmetric particles could make up dark matter in various forms, providing a versatile framework for understanding the unseen mass in the universe. As experiments at the LHC and other facilities continue to probe the nature of dark matter, the discovery of supersymmetric particles would be a major breakthrough. It would confirm long-standing theoretical predictions and provide a clear link between the mysterious dark matter and the deeper structure of the universe. Future experiments in particle physics will play a crucial role in solving the mystery of dark matter. With new advancements in technology and larger, more powerful detectors, scientists are closer than ever to identifying the particles that make up this invisible matter. One of the major focuses will be the continued use of high-energy particle accelerators. The Large Hadron Collider, or LHC, will remain at the forefront of this search. Its planned upgrades will increase the energy and luminosity of its collisions, allowing scientists to probe even deeper into the unknown. If dark matter particles like WIMPs or neutralinos exist, the LHC could potentially create them in its high-energy experiments. In addition to the LHC, other next-generation particle accelerators are being proposed. These include the Future Circular Collider, FCC, and the International Linear Collider, ILC. Both of these would provide more precise measurements and could explore energy scales that are currently out of reach, offering new opportunities to discover dark matter particles. Direct detection experiments will also continue to evolve. These experiments aim to capture dark matter particles as they pass through Earth. Facilities like the Xenon-T and Lux-Zeppelin detectors are using increasingly sensitive technologies, buried deep underground to minimize interference from cosmic rays and other particles. A new approach involves experiments in space. Satellites and space-based detectors, like the Alpha Magnetic Spectrometer on the International Space Station, are searching for indirect signs of dark matter, such as the gamma rays produced when dark matter particles collide and annihilate each other. These could offer vital clues. The hunt for axions, a leading candidate for dark matter, is also ramping up. Experiments like ADMX are specifically designed to detect these light, elusive particles by observing their potential conversion into photons in the presence of strong magnetic fields. If axions exist, these experiments could detect their signature. Neutrino experiments are expected to provide valuable insights into the nature of dark matter as well. Neutrinos, which interact very weakly with matter, are a key part of the puzzle, and future experiments like DUNE, the Deep Underground Neutrino Experiment, aim to study these particles in more detail, potentially uncovering connections to dark matter. The upcoming Euclid satellite, launched by the European Space Agency, will map the geometry of the universe with unprecedented precision. By studying the distribution of galaxies and the cosmic web, Euclid will help scientists measure dark matter's role in shaping the universe's structure and provide data on the effects of dark energy. Future telescopes, such as the Vera Rubin Observatory, will gather massive amounts of data on the movement of galaxies and galaxy clusters. This information will help refine models of dark matter distribution and give scientists a clearer picture of how dark matter influences cosmic evolution. Advances in quantum computing may also revolutionize the search for dark matter. As these systems become more powerful, they could simulate the behavior of dark matter particles and help solve equations that are currently too complex for classical computers. This could open up new theoretical pathways to understanding dark matter. Another exciting development is in the field of gravitational wave astronomy. While gravitational waves are primarily associated with black holes and neutron stars, there is potential for these waves to carry information about dark matter. Future gravitational wave detectors may be able to probe the influence of dark matter on space-time. In the coming years, a combination of particle physics, astrophysics, and advanced computing will bring us closer to uncovering the true nature of dark matter. The results of these experiments could change our understanding of the universe and unlock answers to questions that have puzzled scientists for decades. The cosmological constant theory suggests that dark energy is a constant force, present throughout space, driving the accelerated expansion of the universe. This idea was first introduced by Albert Einstein in his theory of general relativity to explain a static universe, but he later called it his biggest blunder when the universe was discovered to be expanding. However, the cosmological constant was revived in the late 1990s when astronomers observed that the universe's expansion is not slowing down, but accelerating. The constant provides a simple explanation for this acceleration, positing that dark energy is a property of space itself, evenly distributed and unchanging over time. In this theory, dark energy is uniform across the universe, meaning it doesn't clump together like matter or dark matter. Instead, it exerts a repulsive force that counteracts gravity, pushing galaxies apart at an accelerating rate. The cosmological constant fits neatly into the equations of general relativity, offering a straightforward solution. One of the key features of the cosmological constant is that it suggests dark energy has a constant energy density. As the universe expands, new space is created, but the energy associated with dark energy remains the same. This means that even as the universe grows, dark energy continues to dominate the dynamics of cosmic expansion. The cosmological constant is often linked to the concept of vacuum energy. In quantum field theory, even empty space has energy due to quantum fluctuations. This vacuum energy could be responsible for the effects we attribute to dark energy, though the exact relationship between the two remains a mystery. A major challenge for the cosmological constant theory is explaining why the value of dark energy is so small, but not zero. According to quantum theory, the amount of vacuum energy should be much larger than what we observe, leading to a vacuum catastrophe in our calculations. This discrepancy remains one of the biggest puzzles in modern physics. Despite this challenge, the cosmological constant is one of the simplest and most successful explanations for the observed acceleration of the universe. It matches observations of the cosmic microwave background, galaxy distributions, and supernova data, making it a strong contender in explaining dark energy. The theory also has implications for the ultimate fate of the universe. If the cosmological constant remains constant, the universe will continue to expand forever, leading to a big freeze scenario. Over time, galaxies will drift farther apart, stars will burn out, and the universe will become a cold, dark, and empty place. While the cosmological constant provides a clear explanation for the current expansion, it raises deep questions about the nature of space, time, and energy. If dark energy is a fundamental property of space itself, understanding it could reveal new insights into the structure of the universe at the most basic level. There are alternative theories that suggest dark energy might not be constant. In some models, dark energy could evolve over time, changing its strength as the universe expands. These dynamic dark energy theories, such as Quintessence, challenge the cosmological constant simplicity, but offer new possibilities for understanding cosmic expansion. The cosmological constant theory remains the leading explanation for dark energy because of its simplicity and its ability to fit with existing observations. However, the search for a deeper understanding of its origin and nature continues, as physicists aim to resolve the tension between quantum theory and cosmology. As future observations and experiments refine our understanding of the universe's expansion, the cosmological constant will remain central to the discussion. Whether it holds the ultimate answer or points the way to new physics, it is a key part of the story of dark energy. Quintessence is a theory that proposes dark energy isn't a constant force like the cosmological constant, but a dynamic, evolving field. Unlike the static energy density suggested by the cosmological constant, quintessence allows for dark energy to change over time, potentially offering a more flexible explanation for the universe's accelerated expansion. In this model, dark energy is thought to be a scalar field, similar to the field associated with the Higgs boson. This field could vary in strength as the universe evolves, meaning that dark energy might have been weaker or stronger in the past. Quintessence offers a way to account for this variation, rather than assuming dark energy has been constant since the beginning. One of the key motivations behind quintessence is to address the fine-tuning problem of the cosmological constant. If dark energy is dynamic, it could naturally explain why its value is small today, without requiring the precise, unchanging conditions of the cosmological constant. Quintessence provides a mechanism for dark energy to adjust over time. Quintessence models come in two forms: thawing and freezing. In thawing models, dark energy was initially frozen at a constant value in the early universe, and has only recently begun to evolve as the universe expands. In freezing models, dark energy was initially more dynamic, but is now slowing down, approaching a constant value. This evolving nature of dark energy could have important implications for the future of the universe. If dark energy continues to change, the ultimate fate of the universe might differ from the simple big freeze predicted by the cosmological constant. Quintessence opens up the possibility of a more complex and varied cosmic future. Observationally, distinguishing between quintessence and the cosmological constant is challenging. Both models can explain the current acceleration of the universe, but detecting changes in the behavior of dark energy over time would require incredibly precise measurements. Upcoming experiments aim to probe this possibility. One of the ways scientists test quintessence is by studying the rate of cosmic expansion at different points in the universe's history. If dark energy is dynamic, its influence on the expansion rate should have changed over time, leaving an imprint on the distribution of galaxies and the cosmic microwave background. Another potential signature of quintessence could come from gravitational waves. As the scalar field evolves, it might produce subtle effects that influence the propagation of these waves across the universe. Future gravitational wave observatories might detect these tiny variations, providing evidence for dynamic dark energy. Quintessence models can also have different effects on the growth of structure in the universe. If dark energy was stronger or weaker at different times, it could have influenced how galaxies and clusters formed. This could leave observable differences in the large-scale structure of the universe, offering another way to test the theory. The challenge with quintessence is that it requires introducing new fields and parameters that are not yet observed. While it provides a more flexible framework for understanding dark energy, it complicates the picture compared to the simplicity of the cosmological constant. However, it remains an attractive idea because it offers solutions to some of the puzzles that the cosmological constant cannot address. Despite the challenges, quintessence continues to be an area of active research. It provides a dynamic alternative to the static cosmological constant, offering new avenues to explore as scientists search for the true nature of dark energy. Whether dark energy evolves over time is one of the biggest questions facing cosmology today. As future surveys and experiments gather more data on the universe's expansion and structure, scientists hope to determine whether dark energy is constant or changing. Quintessence may hold the key to understanding how dark energy shapes the cosmos and what that means for the ultimate fate of the universe. Modified gravity theories propose that instead of invoking dark matter or dark energy, the laws of gravity themselves might need to be adjusted. These theories suggest that at large scales, or under certain conditions, gravity behaves differently from what is predicted by Einstein's general relativity. This could potentially explain the accelerated expansion of the universe without the need for dark energy. One of the earliest and most well-known modified gravity theories is MOND, or modified Newtonian dynamics. MOND suggests that at very low accelerations, such as in the outer regions of galaxies, gravity doesn't follow the inverse square law. Instead, the force of gravity decreases more slowly, which could explain the flat rotation curves of galaxies without invoking dark matter. While MOND works well on galactic scales, it struggles to explain larger structures like galaxy clusters or the cosmic web. For these larger systems, the presence of dark matter still seems necessary, or a further modification to gravity is required. This has led to the development of more complex theories. One such theory is TeVeS, or tensor vector scalar gravity, which builds on MOND and incorporates elements of general relativity. It allows for both the observed effects on galactic scales and the behavior of gravity on larger scales, but it still faces challenges when compared to the successes of dark matter models. Another approach is the idea of extra dimensions. In certain theories, such as brain-world models, our universe could be part of a higher dimensional space. Gravity in these models might leak into extra dimensions, weakening its influence on large scales and potentially explaining the observed acceleration of the universe. Scalar tensor theories also modify general relativity by introducing additional fields that affect how gravity works. These fields could cause the force of gravity to change over time or vary across different regions of space. Some of these theories are designed to mimic the effects of dark energy while modifying gravity's fundamental nature. There's also FR gravity, where the Einstein-Hilbert action, the equation that describes gravity in general relativity, is replaced by a more general function. This approach modifies the behavior of gravity at large distances and could offer an explanation for the accelerated expansion of the universe without needing dark energy. One of the main challenges for modified gravity theories is matching the precision of general relativity in well-tested environments like the solar system. Any successful theory must not only explain cosmic acceleration, but also reproduce the accurate predictions of general relativity on smaller scales, where it has been thoroughly tested. Testing modified gravity requires precise astronomical observations, particularly of galaxy clusters, gravitational lensing, and the cosmic microwave background. If modified gravity is correct, it should leave distinct signatures in the distribution of matter and the way light bends around massive objects. Gravitational waves offer another promising way to test these theories. If gravity behaves differently on cosmic scales, it could affect how gravitational waves propagate through space. Future observations from advanced gravitational wave detectors may reveal whether these modifications to gravity are needed. Despite the appeal of modified gravity as a way to avoid invoking dark matter and dark energy, most current evidence still points to the existence of these unseen components. Observations of galaxy rotation curves, galaxy clusters, and the large-scale structure of the universe all support the presence of dark matter. However, modified gravity theories remain a vital part of cosmological research. They offer alternative perspectives that challenge our understanding of gravity, space, and time, pushing the boundaries of how we think about the universe. Whether these modifications will ultimately replace or complement the dark matter and dark energy models remains to be seen. Extra dimensions and string theory offer a radically different approach to understanding the universe and its unseen components, including dark matter and dark energy. In string theory, particles are not point-like objects but tiny, vibrating strings, and these strings require extra dimensions of space to exist. These additional dimensions could be key to explaining the universe's most fundamental mysteries. In our everyday experience, we perceive 3 spatial dimensions, but string theory suggests there could be as many as 10 or 11 dimensions. These extra dimensions might be compactified, meaning they are curled up so small that they are invisible to us, but their existence could still affect the way particles and forces behave. One idea is that gravity could be leaking into these extra dimensions. This could explain why gravity is so much weaker than the other fundamental forces, like electromagnetism. If gravity spreads across additional dimensions, its strength in our familiar 3-dimensional space would appear much weaker. In this framework, dark matter might be the result of particles moving through or interacting with these extra dimensions. Some versions of string theory suggest that dark matter could consist of particles that exist in these hidden dimensions, only interacting with our universe through gravity or other weak forces. Brain-world models, which stem from string theory, propose that our universe is a three-dimensional brain embedded in a higher dimensional space. In these models, only gravity can move freely between the brain and the extra dimensions, while other forces remain confined to our familiar space. This could explain why dark matter is so hard to detect directly. Another intriguing aspect of string theory is the possibility of bulk dark matter, where dark matter exists primarily in these extra dimensions. It might interact with ordinary matter only through gravitational effects, providing a new avenue for explaining dark matter's elusive nature and its apparent absence of interactions with light. String theory also provides a framework for unifying the fundamental forces of nature. In this theory, the extra dimensions allow for the reconciliation of quantum mechanics and general relativity, potentially leading to a grand unified theory. Dark matter and dark energy could be natural consequences of this higher dimensional theory. The potential connection between extra dimensions and dark energy is another area of active research. Some models suggest that dark energy could be a byproduct of the geometry of these extra dimensions, influencing the expansion of the universe. The behavior of dark energy might depend on the size or shape of these dimensions as they evolve over time. Testing the existence of extra dimensions is a major challenge. However, scientists are looking for indirect signs. For example, high-energy collisions in particle accelerators like the Large Hadron Collider could reveal the presence of extra dimensions if missing energy or unusual particle behavior is observed. Gravitational waves could also provide clues. If extra dimensions exist, they might influence how gravitational waves propagate through space. Future gravitational wave detectors might detect anomalies in the waves' patterns, hinting at the presence of dimensions beyond the three we know. Despite the elegance of string theory and its potential to explain dark matter and dark energy, it remains highly speculative. Currently, there is no direct experimental evidence for extra dimensions, and testing the theory at the required energy scales is far beyond our current technology. Nevertheless, string theory and the idea of extra dimensions continue to inspire physicists, offering a bold new framework for understanding the universe's most profound mysteries. Whether these extra dimensions hold the key to solving the puzzle of dark matter and dark energy remains one of the most exciting questions in theoretical physics today. Vacuum fluctuations are a key concept in quantum mechanics, referring to the temporary, random changes in energy that occur even in empty space. In the quantum vacuum, particles and antiparticles can spontaneously appear and disappear, creating brief disturbances that influence the behavior of particles and fields. These fluctuations occur because of the uncertainty principle, which states that certain properties, like energy and time, can never be precisely known simultaneously. As a result, even what we think of as empty space is never truly empty, but filled with these fleeting quantum events. One of the most significant roles of vacuum fluctuations is in the concept of vacuum energy, the underlying energy present in all of space. This energy could be responsible for dark energy, driving the accelerated expansion of the universe. In this view, dark energy might arise from the energy density of the quantum vacuum. However, there's a major problem. When scientists try to calculate the vacuum energy using quantum field theory, the result is vastly larger than what is observed in the universe. This discrepancy, known as the vacuum catastrophe, remains one of the biggest unsolved puzzles in physics. Despite this issue, vacuum fluctuations are essential in many well-tested quantum phenomena. For example, they play a role in the Casimir effect, where two uncharged metal plates placed close together in a vacuum experience a small attractive force due to the fluctuations in the quantum field between them. These fluctuations also have implications for particle interactions. In processes like particle collisions, virtual particles from vacuum fluctuations briefly come into existence, influencing the outcome of these events. This shows that vacuum fluctuations are not just theoretical, but have measurable effects on the physical world. In the context of cosmology, vacuum fluctuations in the early universe played a role in shaping the large-scale structure we see today. During the inflationary period, Small quantum fluctuations were stretched to cosmic scales, seeding the growth of galaxies and clusters of galaxies as the universe expanded. The role of vacuum fluctuations is also central to discussions of black hole physics. According to theories like Hawking radiation, these fluctuations at the event horizon of a black hole can lead to the emission of particles, slowly causing the black hole to lose mass and evaporate over time. In addition to dark energy, some theories suggest that vacuum fluctuations might be linked to dark matter. If dark matter interacts with the quantum vacuum in ways we don't yet understand, these fluctuations could provide clues about its elusive nature, helping us detect its presence indirectly. Vacuum fluctuations challenge our understanding of nothingness. They suggest that even the most empty regions of space are alive with quantum activity, influencing the universe at both small and large scales. Understanding these fluctuations could unlock new insights into the fundamental structure of reality. The study of vacuum fluctuations continues to evolve, with researchers exploring their role in everything from particle physics to the expansion of the universe. If we can reconcile the huge predicted energy of the vacuum with the small amount observed, it might lead to breakthroughs in both quantum mechanics and cosmology. Ultimately, vacuum fluctuations remind us that space is not as simple as it seems. These fleeting events, happening everywhere in the universe, may hold the key to some of the deepest mysteries in physics, including the nature of dark energy, dark matter, and the fabric of space-time itself. Direct detection methods are one of the primary ways scientists are trying to find dark matter particles. These experiments aim to catch dark matter particles as they pass through Earth by detecting their rare interactions with ordinary matter. Since dark matter doesn't interact with light, detecting it directly requires extremely sensitive detectors. Most direct detection experiments are located deep underground. This helps shield them from cosmic rays and other particles that could create false signals. By isolating these detectors from everyday radiation, scientists improve their chances of detecting a real dark matter interaction. One of the most advanced types of detectors uses liquid xenon as a target material. When a dark matter particle collides with a xenon atom, it can cause a flash of light or release electrons. Experiments like XenONT and Lux Zeppelin are designed to detect these tiny signals, searching for the telltale sign of a dark matter particle interaction. These detectors are placed in large tanks filled with liquid xenon, and they are surrounded by sensors that can detect the faintest flashes of light or electrical signals. The idea is that when a dark matter particle strikes a xenon atom, it will leave behind a small but detectable trace. Another approach to direct detection involves cryogenic detectors. These detectors are kept at extremely low temperatures, near absolute zero, to reduce thermal noise. If a dark matter particle interacts with the detector, it will create a small vibration or heat change, which the sensitive equipment can pick up. Bubble chambers are another method, where superheated liquid is used as the target. When a particle interacts with the liquid, it causes tiny bubbles to form along its path. These bubbles can be photographed, allowing scientists to study the track left by the potential dark matter particle. Some experiments also use solid-state detectors, which rely on semiconductors like silicon or germanium. These materials produce a small electrical signal when struck by a particle. Experiments like SuperCDMS are designed to capture these signals, focusing on the rare events where a dark matter particle might interact with the detector. While direct detection experiments have yet to find definitive proof of dark matter, they are pushing the limits of what we can detect. Each new generation of detectors is more sensitive, with the hope that one day a dark matter particle will be caught in one of these instruments. The challenge is that dark matter particles, if they exist, interact so weakly with ordinary matter that they pass through most things without leaving a trace. Direct detection methods rely on the rare chance that a dark matter particle will collide with a nucleus, releasing energy that can be measured. The potential discovery of dark matter through direct detection would be a major breakthrough in physics. It would confirm the existence of these elusive particles and help explain the unseen mass that shapes galaxies, galaxy clusters, and the universe itself. New technologies like quantum detectors are being developed to push the boundaries even further. These detectors could be sensitive enough to detect even lighter dark matter particles, opening up new possibilities for discovery. As these experiments continue to gather data, scientists hope that direct detection will eventually provide the long-sought evidence of dark matter. Finding it would not only solve one of the biggest mysteries in physics, but also revolutionize our understanding of the universe's composition. Indirect detection methods focus on looking for the byproducts of dark matter interactions, rather than detecting the particles directly. When dark matter particles collide or decay, they might produce cosmic rays, gamma rays, or other particles that can be observed with sensitive detectors on Earth or in space. One of the primary goals of indirect detection is to observe the annihilation or decay of dark matter particles. If two dark matter particles collide, they could annihilate each other, releasing a burst of high-energy particles, including gamma rays, neutrinos, or antimatter. These signals could provide clues about where dark matter is concentrated. Gamma rays are especially important in the search for dark matter. They are the highest energy form of light and can travel across vast distances without being scattered or absorbed. If dark matter is annihilating in dense regions like the center of galaxies, it could produce gamma rays that we can detect with instruments like the Fermi Gamma Ray Space Telescope. Scientists often focus on regions of space where dark matter is expected to be abundant, such as the Milky Way's galactic center or nearby dwarf galaxies. These areas should have higher rates of dark matter annihilation, making them ideal targets for detecting gamma rays that might be produced by dark matter interactions. Another target for indirect detection is cosmic rays. Cosmic rays are high-energy particles that travel through space, and some theories suggest that dark matter could produce excess cosmic rays, particularly antimatter particles like positrons. Instruments like the Alpha Magnetic Spectrometer, AMS-02, on the International Space Station are designed to detect these excesses. The detection of unusual levels of antimatter, such as positrons, could hint at dark matter interactions. In recent years, AMS-02 has observed an unexpected excess of positrons in cosmic rays, which some scientists speculate could be linked to dark matter, though other explanations like pulsars remain possible. Neutrinos are another potential product of dark matter interactions. These nearly massless particles are extremely difficult to detect because they rarely interact with matter. However, if dark matter annihilation produces neutrinos, they could be detected by massive underground detectors like IceCube, located at the South Pole. While indirect detection is challenging, it offers a way to search for dark matter over large regions of space. By studying the high-energy signals produced by dark matter interactions, scientists can gather indirect evidence of its presence and learn more about its properties. Indirect detection also has the advantage of covering a broad range of potential dark matter masses. Whether dark matter particles are relatively light or heavy, they might produce detectable signals when they annihilate or decay, giving scientists multiple ways to search for them. One of the key challenges in indirect detection is separating potential dark matter signals from background noise. Many astrophysical processes, such as the activity around black holes or supernova explosions, also produce high-energy particles like gamma rays and cosmic rays. Distinguishing between these sources and dark matter requires precise measurements and detailed models. As telescopes and detectors become more advanced, the hope is that we will either detect a clear signal of dark matter or place even tighter constraints on its properties. Upcoming missions like the Cherenkov Telescope Array, CTA, will provide more sensitive measurements of gamma rays, offering new opportunities to detect dark matter indirectly. Though we have yet to find definitive proof, indirect detection remains a promising avenue for uncovering dark matter's secrets. By observing the universe on the largest scales, these methods might eventually reveal the signals we need to understand this mysterious component of the cosmos. The Large Hadron Collider, or LHC, is the world's most powerful particle accelerator, and it plays a crucial role in the search for dark matter. By smashing protons together at incredibly high speeds, the LHC recreates the conditions of the early universe, providing a unique opportunity to search for new particles, including dark matter candidates. One of the primary ways the LHC looks for dark matter is by detecting missing energy. In high-energy collisions, if dark matter particles are produced, they would pass through the detectors without interacting. This missing energy is a key signature scientists are looking for, as it could indicate the presence of weakly interacting particles like WIMPs. The search for supersymmetric particles is also central to the LHC's mission. Supersymmetry predicts the existence of new particles, including the neutralino, a potential dark matter candidate. If these supersymmetric particles exist, they could be produced at the LHC, giving us direct evidence of dark matter. In addition to missing energy, scientists are looking for other indirect signals of dark matter production. These might include specific decay patterns of known particles or the appearance of particles that fit within the supersymmetry framework. These signals could help narrow down the possible properties of dark matter particles. Despite its successes, the LHC has yet to find definitive proof of dark matter. However, each new round of experiments allows scientists to explore higher energy scales and exclude certain models, bringing us closer to understanding what dark matter is or isn't. This process of elimination is just as important as finding new particles. With its upgraded capabilities known as the High Luminosity LHC, the collider will be able to collect more data at higher energies. This will allow scientists to probe even deeper into the unknown, increasing the chances of detecting dark matter or other exotic particles that could explain it. Now, one of the challenges in detecting dark matter at the LHC is that it's expected to interact so weakly with ordinary matter. This means that dark matter particles could be produced in the collisions but would rarely leave behind a noticeable signal. That's why the focus on missing energy is so crucial. It's one of the few ways to infer the presence of these particles. Scientists are also using the LHC to search for evidence of extra dimensions. In certain models, dark matter could interact with these hidden dimensions, affecting how particles behave at high energies. If the LHC detects unusual behavior in particle collisions, it could point to the existence of extra dimensions linked to dark matter. The LHC's search for dark matter is closely connected to the broader quest to understand the universe's fundamental forces. By discovering new particles or interactions, the LHC could help bridge the gap between quantum mechanics and general relativity, potentially revealing how dark matter fits into the larger framework of physics. Even if dark matter is not directly found at the LHC, the collider's experiments are crucial for testing the limits of current theories. Each result, whether positive or negative, helps refine our understanding of particle physics and guides future research in dark matter detection. Other experiments, like those focusing on gravitational waves or cosmic rays, complement the LHC's work. Together, these efforts create a comprehensive approach to understanding dark matter, using different methods to explore its properties from every possible angle. As the LHC continues to push the boundaries of particle physics, its search for dark matter remains one of the most exciting and promising avenues of discovery. The results could reshape our understanding of the universe, providing the missing piece to one of the greatest puzzles in modern science. Dark matter simulations are a crucial tool in understanding how dark matter shapes the structure of the universe. These simulations use powerful computers to model how dark matter behaves over billions of years, helping scientists visualize the unseen matter that governs the formation of galaxies and clusters. One of the most famous simulations is the Millennium simulation, which tracks the evolution of dark matter from the early universe to the present day. By simulating the interactions of billions of dark matter particles, it reveals how dark matter clumps together to form the cosmic web, the vast network of filaments and voids that define the large-scale structure of the universe. These simulations begin with the tiny fluctuations we see in the cosmic microwave background. Over time, dark matter amplifies these fluctuations, pulling in ordinary matter and creating the dense regions that eventually become galaxies and clusters. The simulations provide a way to test how different models of dark matter might influence the growth of these structures. By comparing the results of simulations with real astronomical data, scientists can determine how well different dark matter models match what we observe in the universe. If a simulation using a particular type of dark matter produces results that align with galaxy distributions or rotation curves, it strengthens the case for that model. Simulations also allow scientists to test how different assumptions about dark matter affect the evolution of the universe. For instance, cold dark matter models predict that dark matter moves slowly and clumps together easily, while warm dark matter would spread out more, leading to fewer small galaxies. These simulations help refine our understanding of what dark matter might be. Another important aspect of dark matter simulations is that they help predict where dark matter should be concentrated in the universe. This is essential for both direct and indirect detection experiments, guiding researchers to regions of space like the centers of galaxies or galaxy clusters, where dark matter might be more abundant. The simulations also explore how dark matter halos form around galaxies. These halos are massive, invisible structures that extend far beyond the visible edge of galaxies, holding them together with their gravitational pull. Understanding the shape and size of these halos is key to explaining the motions of stars and gas in galaxies. One challenge with simulations is that they must make assumptions about the nature of dark matter. Different simulations use different models, like cold dark matter, warm dark matter, or self-interacting dark matter, each of which leads to slightly different outcomes. The goal is to find the model that best matches what we observe in the real universe. Dark matter simulations are also helping scientists study galaxy mergers and collisions. By simulating how dark matter behaves during these events, researchers can better understand the role dark matter plays in shaping the evolution of galaxies and clusters, offering insights into both the large-scale universe and individual galaxies. As computing power increases, the resolution of dark matter simulations is improving. This allows scientists to model smaller structures, like dwarf galaxies and subhalos, with greater precision. These small-scale structures are crucial for testing dark matter theories, as different models predict different numbers and distributions of these objects. The results of these simulations not only inform our understanding of dark matter, but also provide insights into the universe's overall history. They help reconstruct how galaxies formed and evolved over time, guided by the unseen presence of dark matter, which has played a critical role in shaping the cosmos as we know it. Dark matter simulations are continually evolving, and future simulations will likely incorporate more complex physics, such as the interaction between dark matter and dark energy. These advancements will further refine our understanding of dark matter's role in the universe, bringing us closer to unlocking one of the deepest mysteries in modern cosmology. Ongoing and future experiments are set to transform our understanding of dark matter and dark energy. These experiments span across particle physics, astrophysics, and cosmology, providing multiple approaches to unraveling the mysteries of the universe's unseen components. One of the most exciting developments is the upgrade to the Large Hadron Collider, which will allow scientists to probe higher energy levels and search for new particles that could be linked to dark matter. Direct detection experiments such as LX-Zeppelin and Xenon-T are continuing to push the boundaries of sensitivity. These underground detectors are designed to capture the rare interactions between dark matter particles and ordinary matter, with hopes that one day they will detect a conclusive signal. Future upgrades will increase their detection capabilities, possibly allowing them to catch even lighter dark matter particles. In space, the Euclid mission, launched by the European Space Agency, will map the large-scale structure of the universe with unprecedented precision. By studying how galaxies and clusters are distributed across the cosmos, Euclid will provide valuable insights into both dark matter and dark energy, helping scientists refine their models of cosmic expansion. The Vera Rubin Observatory, set to begin its operations soon, will conduct a 10-year survey of the night sky. This observatory will gather detailed data on the movement of galaxies and the effects of dark matter and dark energy. By studying these cosmic phenomena in greater detail, it will give scientists new clues about the nature of these invisible forces. The Dark Energy Spectroscopic Instrument, or DESI, is another major ongoing experiment. DESI aims to create a 3D map of the universe, focusing on how dark energy has influenced cosmic expansion over time. With its high precision, DESI will help test different models of dark energy and refine the measurement of the Hubble constant. The James Webb Space Telescope, with its advanced infrared capabilities, will also play a role in the search for dark matter. Webb will be able to look deeper into the universe's history, observing the formation of the first galaxies and how dark matter influenced their growth. These observations could provide important information about the early universe. Gravitational wave astronomy is emerging as a new frontier in the study of dark matter. Future detectors like LISA, the Laser Interferometer Space Antenna, will look for signs of dark matter influencing gravitational waves. These measurements could offer indirect evidence of dark matter's presence in black hole mergers or other cosmic events. Neutrino experiments, such as DUNE, are also pushing forward. Since neutrinos interact only weakly with matter, they offer a parallel to dark matter, and studying them in more detail could reveal connections between the two. DUNE will be one of the most sensitive neutrino detectors, capable of probing the properties of these elusive particles with unprecedented precision. The search for axions, another dark matter candidate, is intensifying as well. Experiments like ADMX are honing in on the possible mass range of axions and refining the detection techniques. If axions are found, they could provide a new solution to the dark matter puzzle and open up new areas of theoretical physics. Another exciting development is the advancement of quantum sensors. These ultra-sensitive devices could be used to detect incredibly faint signals from dark matter particles, allowing scientists to probe interactions that are currently beyond reach. As quantum technologies improve, they could revolutionize the way we search for dark matter. In the coming decades, the combination of these experiments, alongside theoretical advancements, will likely bring us closer to understanding the true nature of dark matter and dark energy. Whether through direct detection, astrophysical observations, or new particle discoveries, the ongoing and future experiments represent humanity's best chance to answer these profound cosmic questions. The results from these experiments have the potential to reshape our understanding of the universe. By unlocking the mysteries of dark matter and dark energy, we'll be uncovering some of the deepest secrets of the cosmos, shedding light on the forces that have shaped the evolution of the universe since its very beginning. The lack of direct detection methods for dark matter has been one of the most significant challenges in modern physics. Despite decades of research and increasingly sensitive experiments, no definitive dark matter particle has yet been observed interacting with ordinary matter. This raises profound questions about the nature of dark matter and whether our current theories need to be rethought. One reason for the absence of detection could be that dark matter particles interact even more weakly than we anticipated. The particles might pass through ordinary matter without leaving any trace, making them extremely difficult to capture using existing technology. This would mean we need detectors that are far more sensitive than those currently available. Another possibility is that dark matter particles are much lighter or much heavier than we've expected. Many direct detection experiments are tuned to look for particles within a specific mass range, often based on the assumption that dark matter particles are WIMPs. If dark matter lies outside this range, our current detectors might not be equipped to find it. It's also possible that dark matter particles interact in ways that we don't yet fully understand. If their interactions involve forces beyond the standard model of physics, they might behave in ways that evade detection through conventional means. This could mean that entirely new approaches are needed to uncover their presence. The lack of direct detection has prompted some scientists to explore alternative dark matter candidates, such as axions or sterile neutrinos. These particles would interact even more weakly with matter than WIMPs, requiring new and innovative detection methods. Experiments specifically designed to hunt for these alternatives are now underway. There's also the question of whether dark matter interacts with ordinary matter at all, outside of its gravitational effects. If dark matter only influences the universe through gravity, as some theories suggest, then direct detection may simply not be possible. In this scenario, indirect methods like studying cosmic rays or gravitational waves could become even more crucial. The failure to directly detect dark matter has led to a deeper exploration of modified gravity theories. Some physicists propose that instead of unseen particles, the laws of gravity may need to be revised at large scales. This could explain the effects we attribute to dark matter without requiring the existence of new particles. At the same time, the search for dark matter continues to push the limits of what is technically possible. New generations of detectors, like those using quantum technologies, could one day reach the level of sensitivity needed to finally capture the elusive dark matter particles, if they exist within our current frameworks. The lack of detection doesn't mean that dark matter doesn't exist. It simply means we may not yet fully understand its nature. Astrophysical evidence, from galaxy rotation curves to gravitational lensing, overwhelmingly supports the existence of dark matter. But finding the exact particles responsible for these effects remains elusive. This ongoing mystery has motivated scientists to think more creatively about how to detect dark matter. New ideas, from novel materials to advanced computing algorithms, are being developed to explore different avenues of detection. The hope is that by widening the search, we will eventually uncover the elusive dark matter signal. While the lack of direct detection can be frustrating, it's also a reminder of how much we have yet to learn about the universe. The search for dark matter is pushing the boundaries of both theoretical physics and experimental technology, and even the absence of evidence is helping refine our understanding of the cosmos. As new experiments come online and theoretical models evolve, the search for dark matter will continue to be one of the most exciting frontiers in science. Whether through direct detection or new theoretical breakthroughs, the effort to uncover the nature of dark matter remains a central focus in the quest to understand the universe's hidden structure. Current models of dark matter and dark energy face several problems that challenge our understanding of the universe. While they explain many observations, such as the movement of galaxies and the expansion of space, they also leave significant gaps that remain unsolved. These unresolved issues push scientists to continually refine and question our models of the cosmos. Now, one of the most prominent issues is the small-scale crisis in cold dark matter models. Simulations based on cold dark matter predict far more small galaxies around larger galaxies than we actually observe. This mismatch between predictions and reality suggests that there may be something missing in our understanding of how dark matter behaves on small scales. Another problem is the nature of dark energy itself. The cosmological constant model, which suggests dark energy is a constant force throughout space, fits the data well, but doesn't explain why its value is so small compared to predictions from quantum mechanics. This enormous discrepancy, known as the vacuum catastrophe, is one of the biggest challenges in modern physics. There is also tension between different measurements of the Hubble constant, the rate at which the universe is expanding. Observations of the early universe, such as the cosmic microwave background, suggest a lower expansion rate than measurements from supernovae and nearby galaxies. This inconsistency might indicate that our current models of dark energy or gravity need revision. Another issue arises with the distribution of dark matter in galaxy clusters. Observations of gravitational lensing show that dark matter might be more spread out in some clusters than predicted by simulations. This raises questions about whether dark matter interacts with itself or with ordinary matter in ways we haven't yet detected. The missing satellites problem adds to the challenges of cold dark matter. While models predict that large galaxies like the Milky Way should be surrounded by many more small satellite galaxies, observations show fewer than expected. This suggests that either our models of dark matter are incomplete, or other forces are at play in galaxy formation. Warm dark matter has been proposed as a solution to some of these problems. It predicts fewer small structures, aligning more closely with observations. However, warm dark matter struggles to explain other aspects of cosmic structure, leaving it as an incomplete alternative. The lack of direct detection for dark matter particles also presents a significant problem. Despite extensive efforts with highly sensitive detectors, no dark matter particles have been found. This has led some scientists to consider more exotic possibilities, like dark matter made of axions or interacting with unknown forces, but these ideas remain speculative. Additionally, modified gravity theories offer an alternative explanation to dark matter by suggesting that the laws of gravity themselves need to be revised. While these theories can explain some observations, such as galaxy rotation curves, they struggle to account for the full range of evidence that supports dark matter, particularly in galaxy clusters. The nature of dark energy poses its own set of questions. Some models suggest that dark energy might not be constant, but could evolve over time. Known as quintessence, this dynamic dark energy could explain some of the tensions in current measurements, but it requires introducing new fields or particles which have yet to be observed. Cosmic simulations based on current models also highlight areas of uncertainty. While they match large-scale structures well, they struggle with details at smaller scales, such as the exact number and distribution of galaxies. These discrepancies suggest that our models might need more complexity or entirely new physics. The interplay between dark matter and dark energy remains one of the biggest mysteries. Current models treat them as separate entities, but it's possible that they are connected in ways we don't yet understand. Uncovering this connection could reshape our entire view of the universe's evolution. In light of these challenges, the pursuit of better models continues. As new data is gathered from advanced telescopes, detectors, and simulations, scientists are constantly refining their theories, seeking a model that can resolve these problems and bring us closer to a complete understanding of the universe. The cosmological constant has been one of the simplest and most widely accepted explanations for dark energy, but it presents several significant issues. One of the biggest problems is known as the fine-tuning problem, which refers to how incredibly small the value of the cosmological constant must be to match observations. According to quantum field theory, the vacuum energy should be much larger than what we observe, leading to a vast discrepancy between theory and reality. Another major issue is the coincidence problem. This problem arises because the densities of dark energy and matter in the universe are roughly the same today, even though they evolve differently over time. It seems unlikely that we are living in a moment when these two values are comparable, raising questions about why the cosmological constant should have just the right value to produce this balance. In addition to these theoretical concerns, the cosmological constant doesn't offer an explanation for why dark energy should behave exactly the same across all of space and time. The constant assumes that dark energy is uniform and unchanging, but we have no fundamental reason to believe this must be the case. There could be more dynamic forms of dark energy that evolve with the expansion of the universe. The cosmological constant also struggles to explain the early universe. During the inflationary period, a form of dark energy drove an extremely rapid expansion, which ended long before the present era of accelerated expansion. The cosmological constant doesn't provide a natural connection between these two phases of cosmic acceleration. Moreover, the cosmological constant doesn't account for possible interactions between dark energy and other components of the universe, such as dark matter or regular matter. If dark energy does interact in subtle ways, we may need a more complex model than a simple constant to describe these interactions. Another challenge is that the cosmological constant cannot explain why the current rate of acceleration is so specific. If dark energy had been slightly stronger or weaker, the universe would have evolved very differently. The delicate balance we see suggests that something more than a constant may be at play. The vacuum catastrophe remains a central issue for the cosmological constant. The value of vacuum energy calculated by quantum mechanics is about 120 orders of magnitude larger than the value of the cosmological constant inferred from observations. This extreme mismatch is one of the most dramatic unsolved puzzles in theoretical physics. Additionally, while the cosmological constant fits current observational data quite well, it doesn't predict anything new. It's a model that works but doesn't provide deeper insights into the nature of dark energy, or offer testable predictions that could lead to breakthroughs in our understanding. Some alternatives to the cosmological constant, such as quintessence, suggest that dark energy could evolve over time. These dynamic models provide a way to explain the coincidence problem and offer a more flexible approach to understanding how dark energy might influence the universe differently at various stages of its history. The simplicity of the cosmological constant is appealing, but it may be too simple. If dark energy is more complex than we currently believe, relying on the cosmological constant alone could be limiting our ability to explore deeper, more nuanced models of the universe's expansion and structure. Despite these challenges, the cosmological constant remains a useful tool in cosmology. It serves as a baseline for more complex models and helps frame our understanding of dark energy within the broader context of general relativity. But solving the problems associated with it is likely to require entirely new physics. As we gather more data from future observations, experiments, and theoretical advances, the hope is that we can resolve the issues with the cosmological constant and either refine the theory or replace it with a more comprehensive explanation for the accelerating expansion of the universe. The Hubble tension problem refers to the growing discrepancy between different measurements of the universe's expansion rate, known as the Hubble constant. Observations of the early universe, such as those from the cosmic microwave background, suggest a lower expansion rate than measurements taken from nearby galaxies. This inconsistency challenges our current understanding of cosmology. The Hubble constant is crucial because it helps describe how fast galaxies are moving apart as the universe expands. The difference in values, one based on early universe data and the other on local measurements, suggests that something fundamental about our cosmological models might be missing or incomplete. One method for measuring the Hubble constant comes from the Planck satellite, which studied the cosmic microwave background. This provides a view of the universe as it was around 380,000 years after the Big Bang. Using this data, scientists calculate an expansion rate of around 67 kilometers per second per megaparsec. On the other hand, measurements from type Ia supernovae and Cepheid variable stars give a different value. These more recent cosmic phenomena suggest a faster expansion rate, closer to 73 kilometers per second per megaparsec. This gap between early and late universe measurements is what we call the Hubble tension. One possible explanation for the tension is that we might not fully understand dark energy's behavior. If dark energy evolves over time, it could affect the expansion rate differently at various points in cosmic history, leading to the different values we observe today. Another explanation could involve new physics beyond the standard model. Some researchers speculate that the universe might contain unknown particles or forces that influence the expansion in ways we haven't yet detected. These hidden factors could be altering the universe's expansion rate over time. Modifications to the theory of gravity itself have also been proposed. If the laws of gravity operate differently on very large scales, this could explain the Hubble tension. Adjusting our understanding of gravity might bring the two measurements into closer alignment. There's also the possibility that systematic errors in one or both methods could be contributing to the discrepancy. While each measurement technique is extremely precise, the slight differences in how data is collected and interpreted could lead to inconsistent results, though most researchers have worked hard to rule out this possibility. Efforts to resolve the Hubble tension are ongoing. Upcoming observations, like those from the James Webb Space Telescope, could provide more accurate data, allowing scientists to better refine the expansion rate and explore potential solutions to the problem. These observations will be critical in resolving this cosmological puzzle. The Hubble tension isn't just a minor issue. It has the potential to reshape our understanding of the universe's fundamental properties. If the tension persists, it could point to new physics that fundamentally changes how we view dark energy, dark matter, or even the fabric of space-time itself. While the exact cause of the Hubble tension remains unknown, it represents one of the most pressing mysteries in modern cosmology. Solving it could unlock deeper insights into the early universe, the nature of dark energy, or the underlying forces that govern cosmic expansion. As new technologies and observational techniques improve, scientists hope to narrow the gap between the different measurements. Whether through new data or new theories, the resolution of the Hubble tension will likely provide profound implications for our understanding of the universe's past, present, and future. Future observations are key to resolving many of the mysteries surrounding dark matter, dark energy, and the expansion of the universe. With new telescopes, detectors, and advanced simulations, scientists hope to gather more precise data that could refine existing models or point to entirely new physics. One of the most anticipated instruments is the James Webb Space Telescope, which will offer unparalleled views of distant galaxies and the early universe. The Vera Rubin Observatory will also play a crucial role. By mapping billions of galaxies over the next decade, it will provide detailed data on the large-scale structure of the universe. This could help to clarify how dark matter is distributed and how dark energy is influencing cosmic expansion over time. Gravitational wave observatories like LISA, the Laser Interferometer Space Antenna, could offer insights into both dark matter and dark energy. Gravitational waves might reveal interactions or phenomena that don't show up in traditional light-based observations, offering a new way to probe the unseen components of the universe. The Euclid mission, launched by the European Space Agency, will specifically focus on dark energy and the geometry of the universe. By studying the distribution of galaxies and galaxy clusters, Euclid will provide critical data that could help distinguish between different dark energy models, including the cosmological constant and dynamic alternatives like Quintessence. Future particle accelerators, such as the proposed Future Circular Collider, could probe higher energy levels than the current Large Hadron Collider. This might lead to the discovery of new particles that could explain dark matter or shed light on the unification of forces in the universe, offering a more complete picture of the cosmos. Advances in quantum sensors could open entirely new possibilities in detecting dark matter. These ultra-sensitive devices might be able to pick up faint interactions that are currently beyond the reach of existing detectors. As this technology improves, it could help detect particles that interact even more weakly than previously imagined. The Dark Energy Spectroscopic Instrument, DSI, is another important project. By mapping the positions of millions of galaxies, DSI will offer detailed information on how dark energy has influenced the universe's expansion over time. This could be vital for resolving tensions in our measurements of the Hubble constant. In addition to these large-scale projects, advances in computational power will allow scientists to run more detailed and accurate simulations of the universe. These simulations can test different dark matter and dark energy models against real data, helping researchers refine their theories and identify which models best match observations. Direct detection experiments will continue to evolve, with upgrades to current detectors and the development of new technologies. These experiments, such as Xeno-NT and LUX-Zeppelin, may eventually reach the sensitivity needed to detect dark matter particles, shedding light on this invisible but critical component of the universe. Space-based observatories like the Fermi Gamma Ray Space Telescope will keep searching for indirect signals of dark matter, such as gamma rays produced by dark matter annihilation. Any unexpected excess of these high-energy particles could provide important clues about dark matter's behavior and properties. Ongoing improvements in neutrino detection, with experiments like DUNE, could reveal connections between neutrinos and dark matter. Since neutrinos interact only weakly with ordinary matter, studying them in greater detail could lead to breakthroughs in understanding other elusive particles, including those that make up dark matter. As these future observations unfold, they will provide critical tests for existing models and may open the door to new discoveries. Whether through the detection of dark matter, insights into dark energy, or refinements in our understanding of cosmic expansion, the next generation of experiments holds the promise of answering some of the universe's most profound questions. In this video, we've journeyed through the vast mysteries of dark matter and dark energy, two of the most elusive and important forces shaping our universe. We started by exploring the foundations of what dark matter is, how it differs from the ordinary matter we're familiar with, and the critical role it plays in the structure of galaxies and galaxy clusters. We also examined what dark matter is not, dismissing the possibilities of it being made up of conventional objects like stars or planets. We then delved into dark energy, the force driving the accelerating expansion of the universe. From the cosmological constant to quintessence, we explored the different theories that attempt to explain this mysterious energy. Understanding how dark energy works remains one of the greatest challenges in modern physics, and we discussed how it might determine the ultimate fate of the universe. We looked at the evidence for dark matter through phenomena such as galaxy rotation curves, gravitational lensing, and the cosmic microwave background. These clues provide indirect proof of dark matter's existence, even if we haven't yet detected it directly. The bullet cluster and the study of galaxy clusters provided further compelling evidence that dark matter exists, and that it plays a massive role in shaping the cosmos. Our journey took us into the world of particle physics as we explored candidates like WIMPs and Axions, and discussed the role of supersymmetry in the dark matter debate. We touched on ongoing experiments, from the Large Hadron Collider to underground detectors like Xenon-T, which are attempting to directly capture these elusive particles. We also addressed some of the major challenges that current models face, including the fine-tuning issues with the cosmological constant and the Hubble tension problem, which suggests we may not fully understand how the universe is expanding. These problems push the boundaries of our current understanding and suggest that new physics may be needed to fully explain the cosmos. Looking ahead, we discussed the role of future experiments and how they might bring clarity to these open questions. New telescopes, space missions, and detectors are all poised to provide deeper insights into dark matter, dark energy, and the large-scale structure of the universe. Through all this, one thing is clear. While we've made incredible strides in understanding the universe, we are still in the early stages of uncovering its deepest secrets. Dark matter and dark energy remain some of the most profound mysteries in science, and solving them will likely lead to revolutionary changes in our understanding of physics. As more data is collected and new experiments are launched, we are closer than ever to discovering the true nature of the invisible forces shaping our cosmos. Whether through direct detection, improved cosmic measurements, or entirely new theoretical models, the answers are out there, waiting to be found. If you've enjoyed this deep dive into the mysteries of the universe, be sure to like this video and subscribe to our channel. Your support helps us bring more content like this, where we explore the wonders of science, physics, and astronomy. And don't forget to check out the rest of the videos on our channel, where we cover everything from black holes to quantum mechanics. There's so much more to learn, and we'd love to have you on this journey with us. Thanks for watching, and we'll see you next time.